Good morning, sir. Good morning, ma'am. Good morning, Rajesh.
Good morning, sir. Hello, good morning, all.
Good morning, ma'am.
Good morning. So we'll start at 10:30, na?
Yes, ma'am.
Yeah, I'm joining. I'm here,
Yes, yes.
but I'll be on seat at 10, around 10:30. It's okay?
Okay, ma'am.
Okay.
So, Rajesh, how was the last day?
Sir,
कैसा रहा कल का दिन?
कल का दिन ठीक रहा सर.
अच्छा अच्छा, एंजॉय किया? चलो ठीक है. YouTube में ज़्यादा लोग ज्वाइन नहीं कर रहे हैं.
हाँ सर, YouTube पे ज्यादा लोग तो नहीं है सर.
6-7 लोग हैं. अच्छा, वो कोई क्वेश्चन आता है कि YouTube पे पोस्ट करते हैं क्या?
नहीं सर, कोई भी क्वेश्चन नहीं आया सर कल से.
अच्छा, अभी बोल देना कि भैया ज्वाइन कर ले सारे लोग, है ना?
ठीक है सर.
हेलो प्रकाश.
हेलो सर, गुड मॉर्निंग सर. गुड मॉर्निंग सर.
कल कितने पार्टिसिपेंट थे इसमें यूट्यूब में?
सर यूट्यूब में कम ही थे सर, 100 करीब रजिस्टर किए, बट अराउंड 10-15 करीब होंगे सर. एम आई करेक्ट राजेश?
यस सर.
सर इस बार एडवर्टाइजमेंट ज़्यादा नहीं हो पाया तो पार्टिसिपेंट कम है. लास्ट टाइम 2800 थे, तो अराउंड 300-350 ज्वाइन रहते थे यूट्यूब पर.
अच्छा.
वो 10% अराउंड ही ज्वाइन होते हैं सर.
हाँ.
रिमेनिंग जस्ट फॉर सर्टिफिकेट.
ओके.
अभी भी सर सर्टिफिकेट की क्वेरीज आई हैं सर, मेल पे रिप्लाई आया है कि मिलेगा कि नहीं.
अभी होल्ड पे रखो, कुछ मत बोलना. अच्छा, ये पॉसिबल है देखना कि कौन कौन ज्वाइन कर रहा है यूट्यूब से?
सर ये पॉसिबल नहीं है सर.
अच्छा.
काम कर सकते हैं, गूगल फॉर्म हम शेयर कर सकते हैं इसमें लिंक.
हम्म.
तो यूट्यूब पे उसमें अपनी आज की इंफॉर्मेशन फिल कर दे तो इससे अटेंडेंस हो जाएगी.
एक्चुअली में क्या, मैडम ने मना किया है सर्टिफिकेट के लिए, तो वर्स्ट केस में देना भी पड़ा तो अगर जो लोग व्यूअर हैं असली 5-6 लोग, उन्हीं को दे दें और क्या, अगर मान लो देना ही पड़ा, किसी ने ऊपर से बोला तो. गुड मॉर्निंग संदीप सर.
गुड मॉर्निंग ओम.
Sir, we will start approximately about 10:30.
Yes, sure. I joined just before
Yes,
that. I should get some time for comfortable with the environment.
fine.
Yes. Just
हेलो, गुड मॉर्निंग.
good morning, sir. My audio is clear, no?
Yes, sir. It's loud, very clear.
Okay. Thank you. On YouTube, it is on YouTube. This session is live, right?
Yes, sir.
Can you just share that link? Okay.
Rajesh, can you share the
Okay.
link on chat? Sir, link will be sufficient, or I should write a send a mail?
If you share with mail, then I can share with my teammates.
Okay.
They can
Sure, sir.
share. Yeah. Okay. You got, no? Okay.
Recent. So please check if it is not you received in inbox. Please check the spam, because our university URL is very long. Hello, everyone.
Hello.
Yeah.
Morning, Mr. Sandeep. Yeah, this is Aruna Tiwari.
Yes, madam. I know. I had seen you. Good morning.
Hello, Mr. Sandeep. This is Dr.
Good
Neha.
morning.
I think I dropped the email to you.
Yes, Neha.
Hello.
Thanks for accepting our invitation.
No, madam. It's my pleasure that your event is going good, and I'm getting the opportunity to represent my work to the people.
So, Prakash, let's start.
Yes, ma'am. Sure. So good morning, everyone. So today's talk is by Mr. Sandeep Malviya. So Sandeep Malviya is a joint director at High Performance Computing Medical and Bioinformatics Application Group of CDAC, Pune. He received an MTech degree in Computer and Information Technology with gold medal from Savitri Phule Pune University, renowned university. He received Bachelor of Engineering in Information Technology from the Government College of Engineering, Sant Gadke Baba Amravati University. He has more than 14-year experience in working with algorithm development using big data and distributed computing. He has expertise in software development using microservices architecture deployable over cloud platforms. Currently, he is the chief architect of software development of bioinformatic application at HPC MBA group of CDEC Pune. Sir, over to you, sir.
Thank you, Om. I'll just share my presentation. My screen is visible?
Yes, sir.
Yes, sir. Good morning, everybody. I'm Sandeep Malviya from CDEC Pune. The topic of my presentation is designing the solution for exascale genome analysis and the need why we need to design this kind of solution. So before proceeding to the presentation, there is some need to talk about the background of the work and the talk I'm going to give. That India is well known for its diverse population and the varied lifestyle being followed. It results into different life-threatening diseases like cancer, diabetes, and tuberculosis. So in India, there is a lot of patients which are being diagnosed with cancer, then tuberculosis and diabetes. And India is the people where the most of the people are in the poor or middle class category. So the medical budget, everything is affecting the common people of the country. Even in diabetes or hypertension, if we see these kind of diseases, it's a medicine which has to be taken daily. So it's a daily budget added to the poor people. So and this kind of medication cost is also increasing. Also, India is not a country where a lot of people have health insurance. So in case of any emergency surgery, lot of people need to put their a lot of money into the hospital bill. So it affects the lifestyle and their basic saving is gone. So it is very important that in India there is a lot of good infrastructure should be developed for healthcare. Also, there should kind of well advanced research should be there where we can have a cheaper medicine we can develop. Also there should be some medication which in which we can before the disease occur we can predict the diseases, so it should not happen. Because if we study the genomic profiling or different kinds of profiling of a person, then there is a different way by which we can predict in advance that uh, how the people whether the people will be diagnosed with certain type of cancer or not. So the precautions or the treatment can be taken prior, which could be less expensive. These kind of things can be done with the advanced research in the area of life sciences. So to study the genomic data, we need to understand what are the genomics data. So genomic data consists of DNA sequences where the mostly the data is coming from next generation sequencing data. Then omics data, which includes genomics, proteomics, and multiomics. Then microarray data, which helps us to give the insights about the expression of genes. Then protein structural data, where the structural information of protein, X-ray, crystal data, NMR data, and cryo-EM data. So these kind of data which we can study in a particular way. To generate this kind of data, also there is a requirement of huge computing power, storage power. Also to analyze this kind of data, there is a need for different kinds of tool to be developed, and those tools should be fast enough to produce the result in a faster amount of time. So if we see the life science volume of data, so by looking at the first graph, we can see that after 2009, then if we see the cumulative number of data sets, then after 2009 there is a big jump in the data which is being accumulated over the years in case for X-ray data, then whole genome sequencing data, then whole exomic sequencing. So different kinds of data which is being accumulated is increasing day by day, and the storage capacity it is creating a challenge for storing the data. Even though we store the data, then this big data has to be accessed efficiently to analyze the data, because just storing will not make any sense. So even if we see the second chart, then the growth of DNA sequencing has increased a lot in the country. Now sequences are easily available at many institutes and researchers. Also the sequencing becomes comparatively cheaper, which used to be earlier. So what is happening, that this increase in the volume of DNA sequencing data, it is estimated that it will reach up to zettabytes or maybe in more. So this is creating a huge problem for the data storage, retrieval, and when I'm talking about data storage and retrieval, I mean that data should be, when we are retrieving, it should be efficiently retrieved, because in any medium we store the data which can be retrieved, but for processing the data, we need the data should be retrieved easily and efficiently. So different kind of data structures need to be developed which can efficiently store, help us to retrieve the data. So if we see this particular slide, then we can understand that different kinds of genomic study, different kind of genomic study when we do over the data, and the computing complexity. So for comparative genomics, we would require a less computing complexity. But when we move towards like a genome scale protein threading, then constraint based flexible docking, or molecular machine classical simulations, or molecule based cell simulation, if we'll go, then the computational complexity will also increase. So as data is being generated at high scale, it gives opportunity to study data in a more degrees of freedom. I mean, more insights we can extract from the data, but to extract those kind of data, we will require the computing power also. So the data which is being generated, that itself is a one challenge, but to process that data, the amount of computing which will be required, that is also a challenge. So it creates then two challenges to us. One is a storage challenge and one is a computing challenge. So what is the international scenario for this kind of dealing with these kind of challenges? So what happens in at international level, there are various institutes in the world, like National Center for Biological Information, NCBI USA, then European Molecular Biology Laboratory, EMBL, then European Bioinformatics Institute, EBI, and DNA Data Bank, Japan. So these kind of institutes are storing this kind of data, and they are serving a lot of users to access this kind of data efficiently. And the good thing about this thing is that the sequencing data, they make a sync with each other. So is automatically sync between these systems, so that whenever some changes happen at one particular DNA sequencing, some things, suppose something is added, then it is reflected to other things. So here at international level, at somehow data is very well managed, and the raw storage of this kind of data is around more than 273 petabytes, and they are serving around 65 million web requests on a particular day. So on average day, there are 65 million requests they are serving. So this much data is being somehow downloaded or uploaded or accessed from their uh, data bank. So at international level, somehow they are in a good condition. But if we see the Indian scenario, then Indian infrastructure is not up to the mark. So in India also, this, if we want to develop our indigenous solution for this kind of huge data which is being generated, also the knowledge and expertise in India is increasing, the access to supercomputer, this kind of system is also increasing. So this huge data which is being generated by the Indian experts, the scholars are there, but the infrastructure for them is not much there. So Indian infrastructure is not up to the mark at this stage. Also in Indian scenario of available data, there are certain problems are also there. Like in India, the data is in bits and pieces. Like each organization is generating data and storing separately, and hence it is difficult to make the correct inference out of that data. So also the data redundancy due to lack of interconnectivity of the organization. Here the organization are not sync with each other. So for example, I would like to say, like somebody is doing molecular simulations or p53 protein on particular parameter for a particular nanosecond. In this scenario, maybe at some institute also some people also may be doing the same simulation with the same parameter, so the redundant operation is going on. But if there is a proper collaboration mechanism or platform is there, so one, if anybody has already done a particular simulation over certain same parameters, and if data is publicly available, then the other person can directly access that data without actually running the simulation, and he can derive his own conclusion or hypothesis out of that data. So that data redundancy in the operation, also in the storage, is a big problem in the country. Then heterogeneous data is in different format. Many people uh, or different scientists and experts in the country, they are storing their data efficiently in their way at a particular format in their organization. But the other people in the same in our country may be doing the data storage in the maybe in the different format. So if they, even though they want to access each other data, or if we want to sync their data somehow, then that different format may create a problem, because this data will create a problem because there is a lack of standardization country. So due to lack of standardization, data reusability is not easily possible. So in our country there is a need of standardization of data. Also the data is not very quality data or not accurate data, because that data has not curated. So before storing the data for archival, because storage, we say storage is a cheaper, but still it use some cost. So if data is properly curated and we store those curated data, then it may efficiently uh, take a uses of that storage of data. Also the data archival is also issue, because data archival is not just dumping a data, but data should be archived in a particular format, in a particular data structure format, so that it can be efficiently accessed also uh, uh, when it is required. Also that as we have limited storage, so what if, when I'm generating the new data and I have limited storage, then in that case what will happen, I'll discard the old data and on the same storage I will put a new data. But that old data might be available to some else people, so when they will access, so instead of, as it is not available because it is discarded due to it being old, so what will happen, he will generate the data again by himself. So this is creating a lot of wastage of resources somehow. So it gives one conclusion to us that the management and organization of data at central repository is very much important. So there is a need, just to I did all this background, that there is a need for scalable solution over exabytes. Uh, Exabytes means that may in future, we are talking about exabytes right now, but maybe after 20 years, 30 years, this exabyte also maybe it will also scale. So our solution is that even as the scale increases in power in case of compute, storage and network, so our solution would be scalable. Because even though we talk petabytes, terabytes or exabytes of data, it's not that in a one day that data is just dumped to those storage systems over a day. What happens, that data is cumulatively stored and accumulated over that system. So whatever the design we will give, that will not be easily, it will not be easy to replace that system if it is not very well designed. Because then restoring that exabytes or petabytes of data will be very expensive operation, time consuming. Then there may be a lot of issue of data security, data might be compromised during the transfer, many things can happen. So the well designed, well thought scalable solution is a very much needed. So also, so the three challenges which I suggested is a compute challenge, storage challenge and network challenge. So in the compute challenge there are three important things, is that one is the data which is generated at high rate. There is very good data is being generated, but data generation is done using lot of parallel algorithm, MPI based algorithm, many different kind of uh, algorithm which exploit the HPC system and generate the data. But the huge data which is being generated, the data generation is a parallel, but the data analysis is mostly serial. Not much tools are there which can parallelly analyze the data, or data can be analyzed in a distributed fashion. So data generation tools are parallel and producing data at huge rate, but most analysis tools are serial. The second challenge is distributed execution. There is a need for tools which has distributed and parallel execution capacity, because if we see that if earlier the traditional structured storage format was a database, like relational database, we used to store data in that system. Data is a very much efficient data where we have a lot of formatting to data, different indexes are available for efficient retrieval of the data, and lot of operations are already there, like row operation, column operation we can do over that. But now the data which is generated, it is mostly unstructured data. So unstructured data itself is a classical problem, where different kind of unstructured data need a different kind of solution based on the that structure of data. So uh, I- we cannot have a very general solution which will solve the problem for all the unstructured data. So different unstructured data in a particular system require different analysis capability, different algorithm has to be made. Then another organization which is storing, they are having, like astronomy is having their own unstructured data, so there might be different tools data which will work on image processing and so on. So the distributed execution tools will depend on the different system where the data is stored. Then the third point is simultaneous data analysis. So what will happen that the tools may not be efficient. So different, suppose we are running a particular simulation of molecule. So if we have a bigger system, then what can happen, that this, for certain parameters we are running a simulation, then again for the same time of simulation we want to run the simulation over the same molecule, maybe on a different parameter. So these two set of parameters we can run simultaneously. So these kind of things can give us a result which will give a solution in a rapid time frame. So to solve a complete challenges, there are certain solution is available like Hadoop. So Hadoop is a one ecosystem of tools which has MapReduce programming paradigm. So it has like mapper, partitioner, combiner, shuffle sort, and reducer. So in MapReduce we can do the when there is the nature of analysis is like a data application is data single instruction multiple data kind of scenario is there. At that time Hadoop can be very much useful, but in Hadoop there is certain limitations like that. uh, all the mapper, they are reading the data from the disk, pro providing some operation, and again storing the data in the disk format. Then the reducer reads the data from the disk, do some operation, then again write to the disk. So lot of disk based operation is there in MapReduce programming paradigm. So it affects the performance of the tool, though it's a highly scalable, I can say a massively scalable solution, but the disk optimization is not very well done in the MapReduce. So there came a Spark. So Spark is a unified analytics platform. It combines the streaming, graph, machine learning, and sequence analysis on a single platform. It is simplified multi-language programming module. It is interactive, and it support batch processing also. The good thing about Spark is that it is in-memory design. So pipeline multiple iteration on a single copy of data in memory. It has superior performance, and it is a natural successor of a MapReduce. What happened in MapReduce? Generally, suppose if we say AI or machine learning kind of algorithm, if we consider, then what happens if we read the data from the disk, which is initially it will be on the disk only, then it will read in to the memory, then it will do some computation. Then in machine learning we have number of epoch, multiple iteration we are having over the data analysis. So what happens, uh, in case of Hadoop, the data will be again saved back to the disk, and again we will do the processing. It will be highly inefficient. But in case of Spark, once the data we read from the disk and we store in the memory, then we perform a epoch different iterations over the data, maybe 100 epoch, 1000 epoch if we do over that data. then it Spark providing in-memory support, so it will be highly efficient. Once all computation is done, then we will write data back to the disk. So Spark become a very good solution. But what happens in this? So that's why when we designed one algorithm for hydrogen bond calculation using Spark. So just say that we develop hydrogen bond, as everybody know that it is a big data analysis tool to analyze hydrogen bonds in the molecular simulation trajectory. It can analyze the trajectory of PDV, amber, and Gromax. So it is a fast and parallel processing of distributed data. It is fault tolerant. It supports both in-memory and on-disk operation. It is scalable and portable on any distributed computing platform. In hydrogen bond, we use a nearest neighbor approach to optimize the performance. And in hydrogen bonds, uh, the residue and residue water based calculation we did. So in hydrogen what happens, that we are calculating the bond distance and bond angle between the atoms, and if the particular bond distance and bond angle are between certain range, then we call it as a hydrogen bond. So in hydrogen bond, if there is a system, even though we consider small system, so there will be 10,000 or 20,000 residue the molecule, and around them there will be a lot of water molecule. So each computation will be there. So it is a big data problem where there will be each atom should be compared with the nearby atoms to calculate the bond distance and a bond angle. So for that we develop this particular map reduce algorithm, and then later we converted it to Spark based solution for in memory, and we get a better performance using Spark compared to MapReduce. But if we see that this data, so we got a linear speed up over a MapReduce with different data sets, and using this data, what we analyzed this, we scaled this particular solution over 5.5 terabytes of trajectory. We analyze using MapReduce. So we got a good result, uh, but there are certain things when we did benchmarking over terabytes of data, then there are certain things which came to our notice. One thing is that intermediate data. So if I say, so if you see that initially I'm reading a data on a disk, then I'm performing some tasks, then I'm make then data is stored in a distributed memory. So distributed memory against a limited thing. So if the data size is within 100 GB or 500 GB, this distributed memory was serving our purpose. But when we scaled our application to terabytes, so the distributed memory was full, and the data again spilled back to the disk because it was not sufficient to store all data. So, and Spark being fault tolerant and resilient, what it did is store the overfilled data to the disk, and again it reads the data from the disk and whatever the data in the memory both, and it do the next iteration, and this is how it's go on. So when we actually go beyond certain size of a data, then our distributed memory capacity is also full. So when we say that when we want to design a solution for petascale or exascale kind of thing, then the intermediate data, even the filtered data, it will also be in a big size, and it will be itself a big data problem. So we have to systematically solve our algorithm with a particular size so that it can efficiently, we have to divide our problem in a sufficient size so that it will utilize the in memory. And if it is going more than that size, then again instead of making a one problem as a big, we should make a number of problems, big number of bigger problems, and we should run it simultaneously. So that is one lesson we learned from the development of HBAT. The second thing, as I mentioned, it is a saturation of main memory. So main memory is saturated and it starts exploiting the disk, so it affects the performance. Also this result into more disk based operation which is slower. So whatever the performance we are gaining from the parallel or distributed nature of the algorithm, the disk based operation is compromising that performance or efficiency we got. So when we will deal with petascale data or exascale data, then we have to consider all these things, or we have to deal smartly smartly while designing the exascale application or exascale algorithm development. The third, these are the computational challenges. The second thing is the storage challenges for big data analysis. So storage challenge is one. The one important thing in storage challenge is like whether your storage solution user or bytes of size of single file. So number of files and the size of a single file. These both things your storage solution should support. Your storage solution should be it should be highly scalable. So storage of a file of huge size in the scale of 100 gigabytes and 100 terabytes, then your storage solution should provide a very good mechanism for searching and retrieval of file using custom data. Like for example, if you consider, suppose you have a directory and there is a suppose 20,000 or 1 million or 1 lakh files in a particular directory. So now if you do your system normal ls command, it's just full. So if programmatically if you read the directory and iterate over that data, so even the million file iteration takes time. So in case of big data storage, if these kind of situations happen, then your system or storage solution should deal with it. Also data sharing and access control over data, because I had initially said that there should be a collaboration or there should be a one organization is sharing the data with other, or if there is an integrated solution, at the time my data is there and there should my control over the data, whether with whom I want to share, whether I want to keep my data public or whether I want to keep my data as a private, or whether I want to share the data with certain set of users, or the data or the scientists and experts with the my organization or the people who are working with my project. So these kind of facility should be there in the uh, our storage solution, which will provide for a exascale and petascale solutions. Then the data should be compressed, because compression will be extremely important, because this big system when it is storing big data, so what will happen, that your system if doesn't provide the compression, then there will be lot of huge size of storage system will be required. Also if your storage system has to be failover, it will have a redundancy of data, so that in case of failover it should be able to get the data from the different nodes. So if so suppose I have 1 exabyte of storage capacity, I'm designing a solution, but if I'm not going for compression, then at least for it it's redundant.
अच्छा अच्छा okay.
Prakash, your mic is on.
Oh sorry ma'am.
Yeah, please continue, Mr. Sandeep.
Okay, so suppose if you want a active exabytes of solution storage solution we want, and if that's the your system will provide a redundancy or failover scenario, so at least one backup copy of the data will be there on another exabyte. So technically you will require 2 exabytes of solution. But if you go for compression of a data, so it suppose that providing even a 50% compression if it is providing, then within the same exabytes you can achieve the same layer same size of data storage, and the even your cost will not increase. Then the data isolation and privacy, at the storage level my data should be isolated. I mean there at should be no access to my data without my knowledge or without my consent to anybody, even to the uh, admin of admin person who is actually managing my storage data storage. So that should be there. Then data confidentiality and security is very much important. So when I talk about data confidentiality and security, so there are two things, that even data in a transit, that this confidentiality and security should be ensured. Also when data is in rest, so my data should be compressed and data should be confidential. So using encryption we can achieve these kind of things. So there are certain solution which is easily doable in exascale system, and there are certain things which we have to design properly to store to cover the challenges of data analysis in exascale system. So if we see storage file system, so we have to go to the file system level, which kind of actually uh, the file system can support me this kind of enormous scalability of data. So we know block storage, file storage, and the cloud-based object storage. So what is happening that object storage solution, if we see, then it is, if you see the first thing, like uh, if we see the object storage, it is highly reliable and cloud scale secondary solution. Then, and it is a solution which provides me the scalability over more than terabytes and petabytes of data. It is a, there is a latency, certain latency in object storage, but what will happen that if in a cloud-based scenario like exascale system, that there is two scenario, we can design an exascale system as a one centralized storage, or we can have different storage center across the country, and they can talk with each other. This kind of also, this kind of scenario, so it will depend on our design thing. So my object storage system can support me in both scenario. And the good thing about object storage is that it is very suitable for unstructured data. So in case of unstructured data, mostly my genomic data is unstructured data, so it is one suitable. So it is a cloud compatible. So even though some other, if I want to access it over public cloud or some other private cloud, then this kind of interoperability I can achieve with object storage, because cloud storage is also now object storage. So we can the so also there are certain advantages of object-based file system, like system divides the data into separate and self-contained units that are restored in a flat structure with all objects at the same level. So object storage is a flat structured file system. So there is no like our directory based system, like it is a hierarchical file system. So object storage is a flat file system. So there are no folders and subdirectories, those used with file storage. Object storage does not store all data together in a single file. User can set the value for a fixed key metadata with object storage, or they can create both the key and value for custom metadata associated with object. In case of in file storage, if we see right click a file, so there are certain properties of a file. So this is a metadata of a file, but this kind of metadata is a fixed, because suppose my file is a big, so it's not so if I do some certain kind of searching with file in with the content of file, it will be highly efficient with, but certain key and values or some attributes which are there, which are associated with the content of file, if I put it in a metadata, so I need a file system which can give me searching over that metadata. So object storage provides access to custom metadata, and we can, with certain tricky solution, we can actually search over metadata and get the direct access to a file, and then we can extract that file. So these kind of things we can do with object storage. There are different object storage implementation, like MeanIO. MeanIO is an open source solution. It utilizes the Amazon S3 API, which makes it perfect for high scale projects that require super strict security. Then Amazon AWS S3. S3 is one of the pioneer of object storage. It manages gigantic loads of data from all over world across hundreds of industries. Then Shape is again an open source software defined storage platform that implement object storage on a single distributed computer cluster and provides 3-in-1 interface for object, block, and file level storage. So there are different solutions for object storage implementation, but we have it is individual choice of a architecture who will use what. But in our solution we have used MeanIO for object storage implementation, because it's really easy and it is a S3 compatible. So if if we use MeanIO, then the S3 storage, it can directly talk with the Amazon AWS S3, and we can have interoperability among them. So object storage pros are there, that it is reduction in cost due to scale-out nature of object storage. It is less costly to store all your data. The object storage provides a infinite scalability, keep adding data forever. There is no limit. Theoretically, at least, there is no limit. Faster data retrieval due to categorization structure of object storage and lack of folder hierarchy. You can retrieve data much faster. Then greater data analytics. Object storage is driven by metadata, as I suggested. That normal block storage has fixed metadata, but in object storage we can have custom metadata. Like for genomics data, I can say about this, which organism, how many base pairs are there, whatever. So we uh, how many genes are there, how many chromosomes are there in particular file, about how much information is there, we can put uh, in a metadata of a file. So what will happen, that if I have this number of files in my object storage and I want a files with a particular organism only, that sequencing I want, or I want all uh, species of rice sequencing, suppose I am storing the data. So in that case, I in my archival, it will over metadata, I can directly locate from metadata search, I can directly locate the files or the sequence file which are having the rice associated thing. So only those files will be stored. So millions and billions files are there. In that, instead of searching over directly over the content, we will have over metadata, we can search and we can reduce our search space and access space, so it will give a better performance. Then optimization of resources, because object storage does not have a filing hierarchy and the metadata is completely customizable, there are far fewer limitations with file or block storage. So object storage is comparatively optimized compared to file and block storage, but there are certain disadvantages, like object storage cannot be modified. But instead of considering it cannot be modified, it is a natural, because generally sequence data is not modified, because generally the modification happens over transactional data. So whenever the transactions are happening, so their RDBMS or normal block storage will be useful. But analytics data is there, then generally it is read only data. So one time it is written archived, then generally it goes on analysis. So when we consider it compared to the requirement transactional data, yes, object storage is not efficient. But in case of, if we see if we see in the perspective of analysis, then object storage uh, system is very much useful. Then this limitation make the uh, then, as I said, also one, our normal file storage, block storage, we can directly consume over POSIX API, but in object storage, we get access to data over HTTP. But HTTP is a general protocol, anybody can access and any language can consume. So again, it being we have uh, access to object storage over HTTP protocol, then interoperability is again easily available. So, and in cloud requirement, we cannot know that our customer or client or our collaborative industries which is using which language or which technology for accessing a data. So in that case also, this HTTP nature of accessing object storage would be useful, because as a rule of thumb, object storage is based in cases where files do not need to be updated frequently. Only this is one criteria, but generally our data is analysis based data, so we can go for exascale storage system for object storage data. So looking at this object storage challenges of compute and object storage, we had designed one Enva-NGS. Enva-NGS is a workflow environment. We have designed one software, that is Enva-NGS. It is a workflow environment for all next generation sequence data analysis generated for genomics. So Enva-NGS is a workflow environment where numerous tools are loosely coupled to analyze different types of genomics and sequencing data. Unvanges has HPC server at its backend, enabling handling of huge sets of data in series as well as in parallel mode. The key features of Anvayas are powerful automated environments, custom tools to provide novel functionalities, drag and drop functionality to build custom workflows, rule engine which add intelligence to control tools and connectivity, can handle multiple genomes and proteomes at a time, can use a backend parallel supercomputer for rapid execution. So this is the particular interface of Anvaya. So on right side you can see there are list of tools are there which we can drag easily and make our custom pipeline, and we can run this whole pipeline as a whole. I mean, no need to run individual tools. So when pipeline is executed directly, and the framework takes the care for individual execution of individual tools, and the next dependent tools are submitted one after another. So the idea why I'm talking about Anvaya here is that, as I said, that in compute challenges there will not be much tools which will actually scale to exascale, but there are a lot of tools which can scale up to maybe terascale or petascale. And if you have pipeline of those kind of tools are there, so there is a need of that pipeline which will take care, there is a need of a software which will take care for the execution of that pipeline, and that pipeline itself can become an exascale pipeline execution. So Anvaya kind of software can be useful, and this framework we have built at CDAC for genome data analysis. And here the two things are there. The user can make the pipeline for custom pipeline, or also they can use a predefined pipeline. So there are for Anvaya, yes, we have predefined pipelines like reference genome mapping, variant calling, chip-seq analysis, then RNA sequence analysis, de novo genome assembly, and transposon sequence data analysis. So these are the 6 pipelines we have already built. User can directly take a pipeline, make a in parameters based on his research requirement, and directly execute a pipeline. And once the pipeline is completed, user can download the data. Once the pipeline is completed, user is notified over a mail that pipeline is completed. You can log in and take your data. So if these individual tools are, even though they are limited in certain level, I mean, limited scalability is also there, but set of tools become a big computational compute intensive pipeline, and they can exploit the exascale computing very well. So that is one point. And the architecture of Anvaya is simple, that there is a one client which access Anvaya server over a cloud or over HTTP protocol, and this server has user data, there is a database, and this is a main heart engine which actually takes care of management of execution pipeline. And underlying HPC infrastructure is there. It can be terascale machine, petascale machine, or exascale machine, but this machine will be responsible for actual execution of a pipeline. So Anvaya server will submit a pipeline, and the pipeline will be executed. The Anvaya server will monitor the pipeline execution. So even in this scenario, what if you see that the number of users are simultaneously accessing Anvaya server, they are submitting their pipeline, and even though if we have big HPC infrastructure, then a number of pipelines of a one user or number of pipelines of a number of users can be executed simultaneously over HPC infrastructure. So this Anvaya solution is theoretically a solution which can actually exploit the computing power of a exascale and petascale machine very efficiently. And user even in user will not aware that he is actually accessing a exascale or petascale machine or their complexity. It will be everything hidden from the user or the scientist, and he can focus on his core work, research work, and the rest of the thing will be taken care by the Anvaya server. So this Anvaya we have deployed at uh, uh, Param Srishti PDKV Institute Ola, then Param Chava we have deployed at Brazil Technology Institute, then India. These forces at these 4 places and institutes we have already deployed Anvaya. So as we discussed that the Anvaya, then HBAT, then storage and compute capacity. So one thing is clear that when we will deal with the exabytes, there is a need for a system which provide high scalable storage over exabytes. Then there is a need for storage solution which which cloud search list files of millions of user or millions files of a user. Then the system should deal with the computing for legacy software, as updating to OS platform for an application is not feasible. So if we see the third point, the system should deal with the computing for legacy software, as updating to OS platform for an application is not feasible. So if in case of NYFC, that suppose there is this particular tool and I have in Anvaya server and HPC infrastructure, I have, this is a big infrastructure, and here actually pipeline is executing, means here actually tools is executing. Now suppose a particular tool is a old legacy tool, I mean this is a old tool and the current operating system doesn't support this tool, for example, then I cannot downgrade the HPC infrastructure for it, or even it is a very stable infrastructure and the need for this particular tool is that it needs the latest OS updates for the execution of this tool. So in this scenario, I cannot upgrade HPC infrastructure just for that tool. So the legacy software or very new software support over this infrastructure become a challenge because of her particular users particular tool individual demand I cannot satisfy it. So there is a need for one solution which can easily we should able to handle for dealing with legacy or very cutting edge software over the existing uh, HPC infrastructure of petabyte, petascale or exascale, because this will be the stable infrastructure and we cannot easily upgrade or downgrade that kind of system. And there is a need for a system which would provide the support for application tools, but also the pipeline workflow of tools to serve the bigger scientific objective. So in biology, just running one tool don't give a particular insights of a data. We have to run a sequence of number of tools in a particular order or fashion to get a larger to extract a larger computational scientific objective. So this workflow and pipeline execution or automated management of workflow and pipeline execution is very much necessary over exascale computing. So in Indian scenario, there is a need for biologists. They will there the data is being generated from hospital and research labs. Then there is a need for data storage and analytics to obtain the desired information, and it will boost the life science committee. So over when we design a right uh, petascale and exascale system, it will serve the Indian scenario in a very good manner, and it will take India at a greater stage at the world platform. So to build that system, there are a lot of modules which need to be built independently or together, and they can cohesively help the system. Like we would require user interface which will have user management, user profile, history, operation details, then data repository. We will require data deposition, means data upload and retrieval interface, data visualization, because the data for data analysis data has to be visualized in the form of chart. So this should be there to the scientist on his dashboard. Then the submission operation for data deposition, data curation, data standardization, data quality assurance. Then infrastructure, for infrastructure we would require system administration, HPC and storage, then database management like database creation, database functionalities, data security, data confidentiality, then HPC computing tools like analytics tools for development, analytics tool for deployment, then retrieval operation like data cataloging and data downloading. So these are number of modules which has to be built, and it should be scalable for exascale solution to serve the computing challenges of exabytes or petabytes and to serve the million of users uh, per day. That is one requirement. And so the on in a broad perspective, there is one storage challenge, analysis and visualization. So storage we can achieve using object storage. then object storage with meta service for searching, querying over metadata, and storage for upload download. We can handle these things. For analysis, uh, here in the third point I had said that to support the legacy software, uh, the container based solution can be very much useful, because what happens, even when running a particular tool, there are certain dependency of that tool to be installed on operating system. So what will happen when we containerize that application, so all the dependencies are there itself in the container. So when we run that container directly, so there are different container tools like Docker, uh, or Mesos, or many container execution platforms are there. So when we put our tool as in image format in a container and we run it, so every dependency or all the requirements or the context which is required for execution of tool will be available in the container. So the container will be self-sufficient. So our application will directly manage the container instead of going into the tool details. So this way our exascale solution will be very much scalable, and the uh, the person who is actually building the tools will take we will have already take the requirement for that dependency of the tool will be taken in the containerized environment, and our workflow or pipeline will run over those containers. So it will be very it all existing application tools very easily. Then visualization like IGL molecule visualization and our kind of charges. So like in integrated computing engine, there will be three. If we see a layered one, if we see as a layer level, then there will be three layer. One is the base HPC hardware, then there will be cloud or a Kubernetes layer which will handle the containerized application, and there is the application software layer. So for Kubernetes, this is a particular architecture of Kubernetes. So Kubernetes, what it does, along with providing the container runtime, it gives a network accessibility over the tools which is running on a different nodes. Also, it takes care of a resilient and failure scenario, like particular tool is not running. So what will happen to the pipeline? So Kubernetes itself retry that running tool over the same node, or if doesn't run for multiple times in the same node, it will try to execute that particular tool on the next node due to any reason. So this way our pipeline will continue to execute even though certain error happens in a particular node due to any network issue or anything. So this is a very scalable architecture, and when our application are containerized, then running those container application over Kubernetes architecture would be useful. So on HPC, exascale HPC based hardware, if we make a Kubernetes layer and run our environment, it will make a system administration job also easy. The domain specific knowledge of a tool will be already self-contained in the container. So it will make the administration easy, and because in exascale system, uh, this task has to be segregated with the tool specific knowledge will the container, then the administration of the system for exascale computing will be taken by Kubernetes layer. So this will solve the lot of operational issues of exascale system. So also then the storage, object storage and container solution, these kind of things if you want to automate for a user level, then one particular complete application or web-based application for accessing this kind of services to the user should be built, and we can build using microservice architecture. So microservice architecture, there are certain things with microservice, like there is a lot of challenges of microservice for in terms of design, security, testing, then communication of microservice, how microservice will communicate. But even though there are challenge is there, the microservice provides certain advantage, like it gives easy monitoring, cyclic dependencies, managing microservices. It provides fault tolerance, integration testing should be dealt in microservices. So major challenges like development when developing the microservice based application, like development complexity, delivery complexity, and operational complexity. So development complexity means when we will deal integrated computing engine platform for exascale, then we have to think in various approaches with design approaches, implementation guidance, framework libraries, integration and data, build integration and testing, then deliverable complexity in terms of runtime infrastructure, runtime dependencies, environment parity, deployment automation, release strategies, then operational complexity in terms of scalability and performance, runtime monitoring, container technology, lifecycle management, security and resilience. So the broad architecture of ICE will be like, at the backend layer we will have object storage, and to access the object storage we cannot give access to the object storage directly to the user, so we will have storage microservices which will access the object storage directly, and it will give abstracted access to the user, so that data isolation, data compression, data privacy, security should be achieved. then then to efficiently use the object storage, uh, the metadata will has to be accessed, and that metadata will store in the Elasticsearch. So what will happen in this scenario, that if metadata is stored in the Elasticsearch, then Elasticsearch is a in-memory database. So what will happen, that user will first look for metadata in the Elasticsearch. Elasticsearch will give the record or direct pointer to the particular file. So our metadata search will happening over Elasticsearch will be, which will be highly efficient. And if we get a pointer to a particular file by searching over metadata, then that pointer will be given to storage service, and storage service will then again access to the object storage. So object storage in combination with Elasticsearch for metadata and a storage microservice can solve our storage problem very easily. But we have to build and design, implement this solution very efficiently. That will be one thing. But once we done, this kind of things can be easily achieved. Then the user management module will be there, which will take care of user profile, who is user, legitimate user or not, then the access to the user, with whom he can share the data, what are the control of that user have data, then the user belong to which particular organization, then user credit, whether legitimacy of the user, we can all things can be done using user service. Then analysis tools. These analysis tools means this will be the tools which will develop for the it will be the domain specific tool, like for genomics, molecular dynamics, or any agricultural based scenario. Those will be tools will be there, and this microservice will take care for the running of the tools. Then there will be a notification things like that. Once a particular tool is completed, then in case of workflow pipeline, then the next dependent tool has to be submitted to the HPC infrastructure for the execution. So the next tool is submitted, that has to be notified. Once the tool is completed, then the notification will be sent to the dependent tools for execution. So this way we manage, using notification service, we can manage the execution of workflow pipeline very easily. So, and there will be one secured gateway, all communication will happen over the gateway, and there will be a client which will access all our service dashboard with web interface or with mobile access, whichever we design and develop. And with gateway, these services will be accessible. This service will abstract the underlying object storage and HPC infrastructure, and we will get a solution. And these microservices are can be easily replicated or make a redundant service to cope up with the load of the user. So this particular module is a scalable module. This module is a scalable module. Elasticsearch is again a scalable module, and HP infrastructure, whatever maybe petascale or exascale module, if it is there, then that is again a big infrastructure. So the number of clients can be served concurrently at a time with their pipelines, and we can get a very good solution for management of our genomic data analysis of that computation bioinformatics data over that particular scenario. And if this solution is scalable to petascale, exascale, or even if certain more, the will increase further. This particular able to our port with that application which allows user to run multiple analysis tools independently. Object storage would provide solution at exascale level. Then platform like Anvaya for pipeline and workflow-based execution can efficiently exploit the exascale computing machine. Then microservice can be used to integrate tools and storage solution which help in managing and analyzing huge amount of data over exascale computing and storage solution. So this is my talk, and I would like to uh, answer any question if anybody has.
Thank you very much for such informative talks. You discuss about the different tools available with CDAC. So I request participant, if you have any question, please ask.
Yeah, just one question. Like, it's nice to see the integrated tools for bioinformatics analysis and NGS analysis of whole genome sequences. So right now, this Anvaya tool, as you mentioned, so this we have to install in our institute, or it is accessible from our.
Sir, we have two approaches for Anvaya.
Yeah.
One is like you are if you have your own infrastructure at your premises is there,
Yeah.
then you can deploy a server module as well at your infrastructure, and you can give access over the client module. Second one is we at CDAC we can host the Anvaya server, and over client you can access it. So based on the because finally Anvaya will run the all the pipeline and tools on the HPC infrastructure. So somewhere that infrastructure has to be there. So at CDAC level, we are providing. Also, if you want that to be on your premises, because using that you can have control over services, you can manage your own user, which kind of user should be here based on your project requirement to a particular user, or certain type of PhD students will access to that pipeline. So if you host yourself, both solutions we have available.
Mr. Sandeep, we have an excess of Param Siddhi in CDAC, so I think these pipelines are already being deployed in Param Siddhi, right?
Madam, in CDAC, there are number of clusters are there, like Param Siddhi is mostly for AI kind of applications are ported. This Anvaya is dedicated to bioinformatics applications. So what happens that the HPC infrastructure, whatever the tools will be running into the Anvaya, that tools has to be installed to the system first. So that tool are not installed in Param Siddhi, but at our BRA facility at SIDAC, those tools are installed. So we can port Anvaya to the BRA facility, and BRA facility is available to bioinformatics committee in the country. They can access it.
Yeah, that is great because we are doing a lot of whole genome sequencing, and we want to analyze all these whole genome sequences. So we
Yes,
will try to use the Anvaya tools.
yes, sir. Because at our group in SIDAC, we also have one dedicated team who is working on molecular dynamics and genomics data analysis, and they are also doing whole genome sequencing. Now they are doing single cell sequencing, and they were from many years they are doing next generation sequencing. So using their experience only, actually we developed this kind of tool because they needed that kind of platform. So they said that it would be useful for them also and to the community in the country also. And later we converted this environment to the microservices level. So now it is scalable to anything, because if somebody want that we have a solution at our private cloud, and we want this particular solution to be deployed to cloud, so we had to change this architecture, and now it is deployable to cloud also, private cloud also, public cloud also, and private means local in premises HPC infrastructure, both places, all places it can be deployed.
Thank you. It was a very informative talk. Thank you.
Yeah.
Thank you very much.
Thank you, sir.
Thanks, Mr. Sandeep. Quick question because time is up. One question, sometime CDAC developed tools which are being integrated with Ashoka Grid, like whatever pipelining or integrated tools you developed, you got a chance to like deploy those things on Ashoka Grid? Agri tools?
No, madam. In Ashoka Grid, I am not aware of Ashoka Grid, madam, because I'm not aware about it.
Okay, it's okay.
Yeah.
Okay, maybe some other group is working for agri domain in your CDAC.
Yes, madam, it might be. But HPCMB group, we are mostly working in like organism-based scenario. So we had a collaboration with ISRI. There we actually deployed ISRI for their purpose. So they actually use at ISRI and NABI. And now we develop a next version of Anvaya. So we had a discussion with ISRI and we are going to deploy the latest Anvaya update to their system, because 2 times we had deployed at ISRI.
Okay.
Yeah.
Good. Okay. Thank you. Thank you very much. It's a
Thank you,
nice
madam.
talk in
Thank you
high
very much.
performance computing area.
Yes. Thank you, madam. I'll stop the sharing.
So I would like to introduce our next speaker, Mr. Ashish Ranjan, who is currently working as a joint director in the HPC Technology Department of CDAC Pune. He's leading the solution design and deployment of HPC system under the National Supercomputing Mission. He is the system architect for numerous HPC systems across various academic and R&D organizations in India and abroad. He has been actively working on the next generation of supercomputers for India. He has also worked as a system administrator in the BSS division of Reliance Infocom. Ashish Ranjan received a degree in Information and Communication Technology from Dhirubhai Ambani Institute of Information and Communication Technology, Gandhinagar, Gujarat. With this, I would like to hand over to Mr. Ashish Ranjan for his thoughtful words and proceeding with the keynotes.
Good morning, everyone.
Good morning, sir.
Is my video visible? Because I can't see myself.
No, as of now, it's not visible.
Just a second. I think, yes. I can see.
Video is fine, visible, sir.
Yes. Just a second. I will just share my presentation. So just quickly confirm whether PPT is visible.
Yes, sir.
Yes, it's visible.
Great. And it's full screen mode.
Yeah, correct.
Okay. Good morning, everyone. I am Ashish Ranjan, belongs to HPC Technologies Group within CDAC Pune, and I have been responsible for design and deployment of numerous NSM deployments. You might have heard Param Shivaya, Param Brahma, Param Pravega, various other Param system we have recently deployed, and we have designed ourselves and always had the motto of indigenous deployment and development of supercomputers. And the topic for our presentation is also National Supercomputing Mission towards building indigenous supercomputing ecosystem. And I will be discussing various verticals within this mission and what we have achieved and where our roadmap is. And this may be relevant to many of you who are working and will be using computing resources. So National Supercomputing Mission or NSM, I will be interchangeably using. So this mission is jointly implemented by CDAC and ISC. And the mission is jointly steered by Ministry of Electronics and Information Technology and Department of Science and Technology. As part of this one, there are 4 initial objectives. So deployment of infrastructure of various capacity with cumulative capacity of around 40 petaflop, 30 to 40 petaflop, we were targeting initially, and it was consisting of multiple type of supercomputers, entry-level supercomputers of around 100 teraflop, mid-range of around petaflop, and large supercomputer of something like around one peak system with 10 petaflop. I will discuss where we are in terms of this one, what we have done, and how this plan is moving. So this mission just doesn't restrict to creation of the infrastructure. Other emphasis area is that we will develop some applications strategic for our country. So as per initial plan, there were 5 major application areas to be developed. Part of this one, we are also creating a lot of development. So that also I will be discussing in detail. Other vertical is also human resource development, and as part of that one, initial target was to train around 20,000 professional in the HPC area. So before going to each vertical, I will just give a summary where we are as of now. So as part of initial objective, we were supposed to develop around 30 petaflop supercomputer cumulative capacity. This was to be deployed around multiple sites, but I think those number of sites has reduced, and we are making bigger systems at all these sites. So as per initial plan, there was 3-phase plan. So in phase 1, we were planning to assemble the system in India. Phase 2, we were supposed to manufacture the system in India. And phase 3 was indigenous design and manufacturing of the system. So phase 2, we have almost completed. So as part of that one, we were supposed to commission 24 petaflop of compute power system, and 13 of those systems are operational. 2 systems are at the site, and I think by July end we should be commissioning those also. So phase 1 and 2 will be completed with 24 petaflop computing power. So coming days we are starting our phase 3, and phase 3 systems are based on our own design. So that I will discuss also what is our design. And so 9 more facilities with cumulative compute power of around 40 petaflop are planned. So total computing capacity across phase 1, 2, and 3 will be 64 petaflop against what we have initially planned of 30 petaflop, but within same budget. So just to give you a statistics, what we have been doing on the systems, around all these 13 systems are in production mode. We have already onboarded 4,000 plus HPC users from around 100 plus institutes across the country. We have already executed the 45 plus lakhs HPC job across all these systems. Another vertical, Nsm HRD, as initially mentioned, we have a target of 20,000 skilled manpower to be trained in HPC area. We have already achieved quite a good number. We have already trained 12,400 plus members. So Nsm R&D vertical, we are designing our own system. We have at this solution level, complete solution is developed by CDAC. Architecture has been defined by CDAC. Integration and building components, how it will be done, all has been done by CDAC. So as part of this one, just not only hardware, software ecosystem has also been developed by CDAC for these all systems. Rudra, Trinitra, and multiple technologies and associated things has been also developed as part of this Nsm. Another interesting development is that we are also developing our own indigenous HPC processor also. So I will also be discussing that. So we in the next vertical we have some HPC application apart from that, also ISC had floated one proposal for in the area of HPC. So they have also approved around 100 HPC applications. And this project has already been approved, and those have been already been given computing resources. Coming to Nsm application development part, 6 domain area had been identified earlier, and projects had been approved on that one, and computing resources for that has been already been allocated. So these areas are Nsm platform for genomics and drug discovery, flood forecasting and disaster management, urban environment and weather modeling, seismic data processing for oil and gas, material science and chemistry, and another was added like telecom network. So in a single slide, if I show you how we have started and where we are heading towards, you can see we have started with our indigenous computers within Nsm. We already crossed that Sivaya and Brahma will start in 2020, so that is not visible here. But from 21 onward, you can see Param Sanganak, Paramutkar, Seva, Smriti, Pravega, Ananta, Parul, Ganga. These have been already been commissioned. These are operational. And coming days, we are coming with our own platform, with our own design.
Please switch off your mics.
I see some noise is there.
Rajesh, please mute most of the participants.
Host can mute them if possible.
Yeah, I've done. Yeah, sorry, Ashish. Please go ahead.
No. So Param Siddhi already deployed. I think this is showing 22, but that commission earlier only. And as part of this one, anyway, I will giving you details individual systems. So this is our roadmap, and final system we are seeing that this system will be based on our own processor, board, interconnect. So this system we are targeting around 2024. So this gives you overview of what capability we are building in India in terms of hardware and software. So we will go with each vertical and what are the development inside the vertical. So as part of indigenous development under Nsm R&D, we have developed CDAC Indigenous Rudra server platform. And currently this is based on second generation Intel Cascade Lake processor. I will also discuss what is the further roadmap for this one. Another development is our indigenous interconnect. So HPC just doesn't require compute power. It also required quite good interconnect also. This has various different characteristics like low latency, high bandwidth. So as part of that one, we have already developed Trinetra, and it has 2 variants. One is with Trinetra 8 and Trinetra B. I will also discussing that one. We have also developed our own indigenous software stack. This is mostly adapted from open source only, but we have customized it a lot for serving such a large systems, and many other custom scripts and components, those were not present, and as per our requirement, we have also included in this one. So those things also we will be discussing. And the interesting part, this OHM HPC processor also we are developing. This will be of around 96 core. So I will go through all these 4 components. Rudra server platform, this is our indigenous server platform. So this complete design is owned by CDAC. So this is not just isolated pilot server. We have created a cluster out of this one also. And this cluster is also listed in top SC India. So total peak performance of this one is 126 teraflop, and efficiency is also around 74.6. We had both variant of GPU and CPU in this one, and current listing is based on 4 GPU nodes, each with 2 A100 GPUs. This system has been tested with various benchmarks. So just to qualify this one, these are stable, reliable systems. So we have done and comparison with the other systems also. So that I will also be presenting. So going forward for the Rudra based platform, we have finalized our manufacturing partner. So VVDN has been selected and they have been given order for 6,000 Rudra servers. And these systems will be used for our coming 40 petaflop systems at various institutes. Some of them will be installed at IIT Mumbai, IUSC Delhi, and IIT Madras, and one 20 petaflop system in CDAC Pune only. So just not only servers, other components like liquid cooling, other things have also been tested on Rudra platform, and those have also been those also giving us a good result. And so our systems will be based on liquid cooling only. So final aim is that we will have industry collaboration for development, transfer of technology to Indian OEMs, manufacturing and support. So they will not have to depend on foreign parties for design import of the servers. So we can share our design to them so that we can have indigenous design servers. So just to give you an overview, what kind of system we are talking. So we have Rudra system based on our processor that we have selected, Cascade Lake 1, and another system from the Nsm only. This system is from taken from Brahma installed at ISR Pune, and there we had even higher frequency than current our one, and we have compared the benchmarks. You can see that we are meeting all the benchmarks very closely, and wherever this yellow highlighted things, in fact we are better than that system. So this just to give you overview, and not apart from this HPC application, we have also tested for the cloud applications, enterprise applications, and we have found absolutely neck to neck. And just to make sure that we are also comparing apple to apple, we have considered both Platinum series of processor from Intel for other make and our system. This is the roadmap for our Rudra servers. Rudra 1 is already POC has been done, and main manufacturing is happening for 6,000 servers based on this Rudra 1.0. This is an Intel Cascade Lake based server, and each system is having around 3.68 teraflop, and each can support to 800 GPUs. And these systems can be used for HPC systems and hyperscale data and cloud platform. Then we are moving towards Rudra 2.0, and that development is already in progress. And this is based on Intel Sapphire Rapid. And each system will have around 8.3.2 teraflop. And each can support, this platform can support 4 GPU. And this can be used for both HPC and AI systems, and again for hyperscale data centers and cloud. And additional, since we have more PCIs slots here, so these systems can be used for the storage purpose also. So we have a plan for coming up with our own storage solution for high throughput requirements. And going forward, we have a Rudra 3.0 Ananta is the name for that one. That will be based on our own processor, CDAC own processor. And each processor, not each system will have around 10 teraflop of peak computing, and it will also support 4 GPU. And the similar kind of target audience for this one also. So this is our Trinitra Indigenous HPC Interconnect. As I already mentioned, HPC interconnects are not as like of gigabit Ethernet. It has a different kind of characteristic. It need to have low latency, and some of this offloading also need to be done on the network processor for some computation, some functions. So for that precise reasons, we have developed our own Trinitra A. So this is actually a switchless configuration. So we will have only NIC, and that can be connected over 3D torus topology, and we can scale to thousands of nodes. And this has quite a good throughput of 6 into 100 GPS full duplex each card. And This system is available now. We have already created POC, and so the next slide I will discuss that one. And Trinetra, that is under development, and that will have around 10 into 200 Gbps. So per system we will have a 2 terabyte of per TBps of throughput, you can say, and this will be coming in around October 2022. So Trinetra A, we have already deployed a cluster with 50 nodes and multiple MPI related benchmarks, network benchmark, other than HPC applications benchmark has also been tested, and various optimization tuning has been done on this one. This system is also listed in our top SC with the efficiency of 74%. First trial of Trinetra is successful. And once this our 6,000 systems that we have already ordered, we are planning to 1 petaflop system POC within CDAC, and there we will be deploying this interconnect up to 32 nodes also in that one. So those who are interested in knowing that whether India has our own processor or not, so this is our answer to that. So this development is under progress. So plan to be available in 2024 Ohm HPC processor. So each processor will have 96 cores, and these are based on latest generation ARM 8.4 architecture. It will have around 96 MB of L2 cache and 96 MB of system cache, equivalent to something like L3 cache. It will have 8 channels of 5200 megahertz DDR5 memory. It will also support HBM3 also. So for those high throughput memory requirement, this can be very beneficial. And this will have around 128 lanes of PCI 5, and this will also support CXL. So this multiple coherency related accelerator NIC, those can be supported on this platform. And this will support up to 2 sockets. So on a single node, you can have maximum 192 cores. So considering this servers will be used for many secure or defense projects also. So we have enabled multiple secure board crypto support inside this one. And this will be based on latest generation 5 nanometer technology node. So these are chiplets based. So each processor will have 2 chiplets. So I think I will show you one layout diagram for that one also. So this is targeted for both HPC AI and cloud market. So this dual socket server will finally called Ananta server. So that I already mentioned in the Rudra roadmap. So final Rudra server based system will be called Ananta server. That will be based on Ohm processors. And each node will have 10 teraflop of computing power. And 2024, we are planning to have one pilot system with Ohm processor, the whole cluster of HPC, having around 100 servers of Ananta. And apart from this one, this processor is ours, hardware is ours. So we are also putting a lot of effort on indigenous of software ecosystem also, mostly leveraging the open source component. So we may not have to depend on a third party for some basic softwares also. So we are not very alien to this ARM architecture. So we have already deployed 100 teraflop ARM system based on A64FX Fujitsu from Fujitsu, and this cluster is already operational. And this cluster doesn't have this DDR5 RAM. This is completely based on HBM only. And so we have a reference for also comparison of what we are expecting in near future. So this is the layout of our 96 core Ohm processor. So as I mentioned, these are chiplets based processor. So there are 2 chiplets on a single package. So each chiplet is of 48 cores, and so total 96 core you can have in a single Ohm processor, and associated with DDR channels, PCI slots, and HBM HBM memory controller also. So this is the final specification for our system on chip processor, and as you can see, final package will have 2 chiplets per package, and it will have 96 cores per package, and it will have 16 DDR5 channels, and total DDR bandwidth will be of around per processor will be of 332. So in our Ananta server, eventually it will have around 600 something gigabyte of memory throughput only on DDR. And apart from that, we will have HBM3 configuration also. So that will give us around 3 terabyte of memory performance. So these are very, very large numbers, and that will suitable to many memory hungry applications. And PCI slots also, we will have around 64 lanes per processor. So total 128 lanes will be available. So these systems can be used for many other hosting multiple NICs or multiple storage NVMe kind of solutions. If you want to host or you want to create a custom storage solutions, or want to host multiple GPU nodes. So this will help us. So compute power, I think this is double precision. So this is per processor. So this is 4.92. So if you multiply it by 2, so per server you will have around 9.99. So approx 10 teraflop of compute power. So in terms of byte per flop, this is quite a good jump. So we are achieving around 0.73. This is very, very large compared to many of the competition right now offering, and even the future also they are planning to offer. And package per package or per processor, we are expecting around 300 watt of power. So I think the OHM processor is also on right track, and system architecture has already been finalized. Design partner has been already been selected, and they are helping us to go forward. And this RFP is already under progress. So I think we should be hearing very soon. Apart from this hardware thing, we always emphasize that all our systems will have our own software ecosystem. So as part of that one, we have developed CSCS, CDAC HPC cluster suite. So around 20-27 components are there, and many of them are open source. So right side you can see the yellow one. These are components that we have developed. Because many of the components that we are getting from open source, like mostly monitoring and development, they are not suitable to our requirement, and many times we have to depend on the commercial software. So since we were not opting for the commercial software, so we have developed this software from Avenissio. And these systems, this software ecosystem has been deployed on all 13 large Nsm systems that we have deployed at the various IITs and NITs. One of the key component of this software stack is Chakshu, and you must have heard multiple monitoring softwares, but these all monitoring softwares come with several restrictions, and they all focus on certain aspect. So considering those restrictions, we have developed our own monitoring software, since we have to monitor 15 already, and 9 to 10 systems will be coming in future. We cannot monitor by these kind of monitoring software already available with open source or commercial. So this gives us both view for the user also, and for admin and top management perspective. So this gives me various kind of statistics reporting that helps me which department is using more, which users are allocated, which season the resources are more, what is the wait time, or what, you just name it, all kind of reporting you can do it on a single click. And latest version of Chakshu 1.4 already deployed on Nsm phase 1, phase 2, and multiple other features we are also upgrading, and newer version of Chakshu will be coming soon. Apart from that one, we are also developing several other software. These are mostly developed by our CDAC Bangalore colleagues, and some of them are CDAC Automatic Parallelization Compiler, CAPC. This basically converts your sequential code into parallel code. And they have demonstrated on various Nsm systems also. And then again, their parallel development environment. So this is basically an IDE for hybrid parallel application development, providing ease of use of HPC and mobility to users and data, and various utilities. And then application profiler is also planned as part of this one. So now we are talking that each processor will have around 200 watt to 300 watt, and even say Fire Rapid or many other Intel processor, they are coming. They might be having around 400 watt per chip. So cooling that one through air cooling will be a challenge or impossible. So considering that restriction, we have also invested a lot of effort on cooling aspect, so both at the chip level cooling. So where we have, you can see chip cooler. So this will be on top of this one processor itself, and this outdoor unit where the heat exchange will take from air to water. Nsm infrastructure. So you must have heard multiple Param systems. So this is a single slide that I have mentioned all the systems of various capacity. So Nsm phase 1 consisting of these 5 systems: IIT Varanasi, IIT Kharagpur, IISER Pune, IIT Kanpur, and JNCSR. These systems are already operational in, I think, 2021-20 only. And in subsequent years, we have deployed. In fact, you will be surprised to know that this last 6 to 7 systems have been deployed in last 4 to 5 months. So my team has been very, very busy deploying these many systems and making it operational. And some of them were at ISC, and so they have also tested with their larger cores of around 25,000 cores in a single system. So our stack system has been found very, very stable. And so this experience will also help us create larger systems of 20 or even XI flop systems. And 2 systems still under progress, not have been commissioned. So they will be commissioned very soon. So total 24 petaflop systems we have already commissioned or commissioning by July. So these are the pictures of the systems you must have seen. So this is the IIT Kharagpur left side, Param Shakti. Param Shivai was our first system, and Param Brahma. You might have been seeing a lot of jobs there in 33 lakhs comparison to 5 or 6 lakh job. So IISER, they generally submit many small jobs also and array kind of jobs. So that's the number is very high. And then again JNCSR, Param Yukti we call it, Param Sangnak at IIT Kanpur, and Param Seva recently installed at IIT Hyderabad. Param Smriti, this is also again they are into this agriculture research. Param Smriti, Param at Navi Mohali. And one system, this is dedicated for MSME kind of requirement, Param Utkas at CDAC Bangalore. And this Param Parvega has been installed at ISC, and they are one of the largest user in country. Param Ganga recently commissioned at IIT Roorkee. So Param Parul and Param Ananta already been commissioned. Another system you might have heard is Param Siddhi. This is a dedicated system for AI kind of requirement. And this serves both HPC AI convergence jobs. So HPC jobs can also be submitted. And but major job those been running on this one are mostly AI related, deep learning kind of thing. So NLTM is one of the major users. In fact, half of the computing power they are using currently. So currently on this system, around 175 visits from 20 plus ships have already been accommodated, and around 60,000 jobs have been completed on this system. Param Siddhi. So apart from phase 1, phase 2, and Param Siddhi, we have also some small clusters. So I think my colleague was discussing earlier. So bioinformatics has a specific for their requirement. So they have deployed around 230 teraflop of system. And we have one Sangam lab, 120. So there we have tested all our ecosystem. So dispatching any software to our production systems, all those are tested on our this first second and third numbers systems. And as part of initial plan, we wanted to test on all kind of architectures, just not only Intel. So we have developed cluster based on AMD, Power, and even ARM. So we have experience with all four kind of architecture, and our software, our on CSCS software has been tested on all these four systems. And we found that our software agnostic to any kind of hardware architecture. And as part of phase 3, we are deploying 9 systems, total cumulative capacity of around 40 petaflop. So this will be commissioned coming year, most probably next year only. Another vertical Nsm SRD, as I had mentioned, so total target was 20,000 HPC aware manpower to be made in collaboration with academia industry. So training program conducted so far includes faculty development program, UG and PG courses, workshop, boot camps, hackathons, online courses. We have also developed model curriculum as part of that one, and some of them have been adopted by IITs, NITs, and other colleges. Just for this HPC training part, we have 4 nodal centers that have been established at IIT Kharagpur, IIT Madras, IIT Goa, and IIT Palakkad. And one HPC system, Param Vidya, has been deployed as part of that one. So that will help for the training users on HPC. So we have conducted several online courses for HPC MLDL through a nodal center along with CDAC. We are planning to conduct one SCSC training. I think this has been done since the date is May. Most probably this must have been done. And training of 12,000 users have already been accomplished. So another vertical was that just not infrastructure and skill development, and there has to be some strategic applications. So we should have our own application also. So we are developing so many systems, and we need to have some of our strategic application to be ported on that one, and that should scale to the systems also. So as part of that one, 6 projects have been approved, and first one is the Nsm platform for genomics and drug discovery. Second one is, so I think these are already there in this one. So Nsm platform for genomic and drug discovery, my colleague already discussed this one. So as part of this one, they have already commissioned 2 or 3 small clusters, and all their software tools has been ported on that one. And they're also providing as a service also. So another project is this Nsm Urban Modeling, and objective of this one is that development of an online fully coupled urban meteorology, hydrology, CFD and air quality modeling system to capture the urban representation of micro-scale city environment conditions. So this model has been tested, and this has been deployed on Nsm systems. Another project is that early warning system for flood predictions, and as part of this one, they are doing for Mahanadi Basin, and this system is running in production mode. So flood prediction they are doing through Nsm system. So another one is the seismic Nsm seismic project, and objective is to develop an indigenous software suite for seismic imaging and complex earth structure. And one project has also been added into this one, this MPP lab. This is basically for the telecom, it's kind of telecom optimizer. And just not the application, they are also coming up with a unified architecture, converging all the technology like big data, AI, and HPC. So this is a very interesting development, and this will be used by CDOT. Another aspect of this whole development was that we are using a lot of open source application or still on our HPC system. So optimization of this application systems, porting, tuning has to be done. So we have developed a mechanism. So all these systems come pre-built with various applications, and application list I have not demonstrated, but I think there are multiple domain areas, and we have ported many applications, and those are optimized for this platform. So once a user is given access on Nsm system, he gets ready-made available these open source systems, and he can start using that one. So as part of this one, a lot of effort has been put, and various framework topology technology has been adopted. We have also adopted not only HPC applications, other than DL applications, and whatever not framework also not including to MPI. We have also included container-based systems for effective usage of GPUs. So these have been ported and tested on all our Nsm systems. And not just ported, once the application users require some support also. So this team has been dedicatedly providing support, but since number of users are large, we are focusing on some important applications and critical problems. We are providing support on this one. So that's it from my side. If you have any questions, I'm happy to answer.
Thank you very much. It was a really nice talk, and we all knew about what the CDEC is doing and how advanced level we have reached. I request participant, if you have any question, please ask. I repeat, if anybody has any questions, anybody want to know about the more development in particular area, please ask.
Sir, may I?
Yeah, please.
Thanks. Sir, is it possible to build a supercomputer on mobile phones? Could be iPhone or Android?
No, so you have to understand this mobile processors are very different from HPC processor or server processors. So HPC applications require a lot of precisions and to be done. So those mobile processors are not meant for high precision calculations. They are for low precisions. So if your workload can be done over low precision calculations, you may use. And since they are basically based on the ARM IP, so you can still create a cluster through the, why go with iPhone or other things. You can get some Raspberry Pi and you can create 4 or 5 Raspberry Pi. You can create a cluster out of that one. So low precision applications can be done on those.
But still, sir, we have it has been developed for 48 core chip, like Atlas chip. Atlas chip has been dominated by ARM.
Correct.
For example, for 3D games like that.
Yes.
So it's one kind of augmented reality application.
Yes.
A single chip cloud, SCC.
So no, these developments are there, and we have also adopted ARM. But on top of that one, we have put several other instructions that helps for HPC and this vector processing. So the basic ARM chip instructions doesn't come with those additional instruction sets. So the processor that we are talking is it having a lot of extra capabilities and features that will help for scientific calculations.
Yes. Sir, one more question, sir. The by statistics, latest January 2022, Param Pravega is the fastest supercomputer, isn't it?
No, actually, if you consider, there are 3 more systems also. One is from, I think IITM has installed, they have a Mihir. I think that's bigger than this one. Even Param Siddhi is 5.67 petaflop. So I think Pravega 3rd, 4th number is coming. But under the build approach, this is the largest system, you can say. So this has been completely indigenously developed with our software stack.
Yes, sir. Thank you, sir.
Sir, I have one question, sir.
Yeah,
so you has given information of there's a flood detection system at the Mahanadi.
Yes.
Deployed.
Hmm.
So such kind of work is only the CDEC is a partner, or some other academic institute also
No,
participates?
I think user agency also is part of that one. So and if they are giving for this prediction also, so this has to go through this authority through. So we cannot predict ourselves and broadcast this information. So end user or the government is part of that one. But apart from this one, there are several other projects similar is going on. But this one is in collaboration with the individuals.
So, sir, it's a working or it's a under development?
No, it's a working. I see. In fact, last year during this season, they were running in the production environment. And this year also, they are. In fact, they are using 30-40% of our Param Ganga system or some other systems. So
Okay.
because they run in production mode for 4 to 6 hours.
Okay. So, sir, one more thing, sir. As you have demonstrated the very many indigenous system, so where we are replacing the foreign systems or some outside outsources system nowadays,
No,
because
so I think if I give you a preview, initial objective of this NSM was that we were supposed to buy some systems also, and that was supposed to be bought by ISC, and CDEC was concentrated only on this building of the system. But by seeing the success of this initial implementation with the build approach, government completely scrapped this buy approach, and now all the system has been built. So now you can see most of the system has been built by CDAC in recent years. Even if we have not directly involved, we have been involved as a consultant, and we have tried to at least completely solution point of view, this has been completely owned by us, India, and design is ours, and we are trying to replicate. We cannot replace hardware right now, but coming with our own hardware, we will replace that part also. But software ecosystem has been completely supported and developed by us.
okay, sir, but that's good, but it should be broadcasted more or advertise more that in many areas this we have this indigenous system rather than we are procuring from the outside.
No, I think this publicity of NSM system is quite large. In fact, any HPC users, they are anyway eventually ending up to us only. And if you still feel that some people are not aware, we are anyway conducting a lot of hackathon boot camps, and we will reach to everyone. But I think just not user. In fact, our ecosystem partner, our OEMs, they all know contribution of NSM towards building indigenous supercomputer in this country. Even outside also India, people are very much aware with this progress in this one.
Yes, sir. Being accommodation, I am part of one institute, so I watched some YouTube video of this Vigyan Beer or something which is governed by this government. So I find there's a lack of information that side because there's so much work you are doing, but that is not available on those channels, which our user who's not accessing HPC but want to know what is going on in India. So at that part, so you are true that people who are using HPC, they know, but the others should also know that what is the progress we are doing. Okay, sir. Fine. Thank you.
No, thanks for your feedback. I think we will try to go across the channel also. And since I'm interacting with you now, you can tell them about our system.
Sure,
so this
sir.
way we will propagate.
Yes.
Thank you.
So one more request, sir.
Yeah. Good afternoon,
be-
Ashish Ranjan. I guess you are the in charge of Param Siddhi. We have interacted sometime.
Yeah, no, you came to me. I redirected to Rishi, one of my other colleague. So he's the system admin in charge of that one. But I'm looking for overall routing perspective and design perspective.
So it's not related to your presentation, but I'm talking about like I want to know about the policy if like we are the user of because we funded under this NSM funding scheme from ISC. So in case funds are over, like it is about to over by March, we are able to finish everything. And whatever sanctioned, if we are going to overrun out of it, like overutilize with Param Siddhi, Then what's the policy at your end?
So there is two way. Since you have already shown that you have a interesting application, you will. So you can approach directly to NSM authority. Most probably Satish Vadiyar you can approach, and if some of the I'm just offline since I'm online, I can't say that one. But you can approach him. They have been generous enough. If some projects have not consumed their resource, they may balance it out.
No, he already has given 7 more lakhs of rupees for using this infrastructure, NSM infrastructure. But like as per sanction, it is for 2 years only. Na? So like
no, so that issue is not there. That you can extend because this NSM has been extended till 2024. So these systems are operational. So I think you should get support.
Okay, so we keep on writing if it is overutilized or exhausted. Like it happened with Param Siddhi that it was overutilized, and before 2-3 days I got some mail. We were engaged in this workshop preparation, so we could not see. But as the work is going on exhaustively, my team is working, and I'm guessing that maybe it will overrun before March end. So in that case, we'll again approach to Dr. Vadiyar, as you said.
So if he supports, fine. Otherwise, also you can contact me. We'll try to see how we can accommodate this request.
That's great. That's great. Okay, so we'll directly approach you. Preeti Jha, please note down.
Yes.
Yeah. Thanks a lot. Thanks for joining with us in this workshop and accepting our invitation for this talk.
Thank you. Thanks for giving this opportunity.
Thank you very much. It was very interesting talk.
Thank you.
And we'll meet after lunch at 1:30.
Yeah, Om Prakash, can you circulate a mail to all our organizers for valedictory?
Sure, ma'am.
Just tell them the time for valedictory because Dr. Karthikeyan messaged me 3 o'clock, but Amit and Sanjay from Pilani.
Yes.
Dr. Mitali and Ayan.
Okay, sure, ma'am.
You just tell them the time that this is the time of valedictory after finishing Dr. Ratnapalki's lecture.
So, ma'am, the exact time is 3:10.
Yeah, so we can write 3:10.
Okay.
Maybe 5 minutes before or later. We
Sure.
can write it. Just circulate, remind them so that everyone will be here.
Sure. Thank you.
Yeah, thanks everyone for joining. So it's a break for lunch and then we'll be back by 1:30, na? 1:30 with the...
Yes. Ashish sir.
Ashish sir. Okay, Ashish Tulvekar.
Yes.
Okay. Thank you.
Thank you.
Rajesh, please play that video. Hello, good afternoon, everyone.
Good afternoon. Good afternoon, Ashish sir.
Good afternoon. Om Prakash, we are starting.
Yes, ma'am.
Ashish sir is there.
Yes, ma'am. Sir is there.
Are you able to hear me?
Good afternoon, Mr.
Yes.
Ashish.
Yes, sir.
Are you able to hear me?
Yes, sir. We are able to hear you.
Okay. Just give me a minute. Yeah, good afternoon.
Good afternoon.
So, good afternoon, everyone. Now, our talk is this talk is done by Mr. Ashish Kulvekar, sir. I briefly introduce sir. Sir is currently working as a convener of Nsm expert group on HR development. He obtained his master degree in electrical engineering from VJIT Bombay University. He worked for 9 years with the hardware R&D division of Patni Computer System, Bombay, before joining Hardware Technology Development Group at CDEC Pune. At CDEC, he has been involved in development of hardware subsystem for various generation of Param supercomputing system and also sharing knowledge with student of PG diploma conducted by Advanced Computing Training School of CDEC. He is also involved in coordinating the activities of expert group and implementing its mandate by working with various stakeholders from educational institute and the industry. Sir?
Yeah, give me a
Yeah.
minute. Let me
Yes,
just share.
fine, sir.
Yeah, I'm unable to see the presentation in the share folder. Let me just.
Fine.
Give me a minute. I don't know why it is not showing. Let me just try to share the screen and then. Is it visible?
Yes, sir.
Okay. Anyway, I will also turn on my video. All right. So are we ready to go?
Yes, sir.
Yes,
Okay.
you are visible also.
Okay. Okay.
Thanks for joining this and giving talk on this.
Yeah, my pleasure. So, good afternoon, and I hope everybody had a good lunch. And welcome to this workshop on sustainable agriculture using Bharat Agri-Grid ecosystem. I would be talking about leveraging HPC for agriculture. So, okay. So I have unfortunately not updated this slide. I was too busy in hiding all other slides. So just let's ignore this agenda slide, but we'll begin with introduction and I'll tell you how HPC and ICT. In fact, I had added this and ICT for it. The original talk was this, but I added this and ICT for it because there are quite a few things in ICT that can be used for agriculture. So I will discuss that and we'll end up with the summary. Let's begin with introduction. So as we all know, I mean, this has been said enough number of times during this workshop that agriculture plays a significant role in India's economy, and a vast majority of citizens, they are directly or indirectly connected with agriculture. And that's how this is very important overall for a country. And as we currently at the beginning of monsoon monsoon season, always we find that in the month of May, when the advisory is given, whether the monsoon will be good or not, I mean, we all get a relief when we say that the monsoon is going to be normal. And even things like share market, etc., they also go up and down based on how the monsoon is going to be. So that's the very important role that monsoon plays because it directly affects agriculture. There are some traditional methods that are used by the farmers and for improving the yield, and they have been used for decades. I mean, that's the traditional way of doing. They will put manure, they will have good seeds and all those things. That is the basic principle on which agriculture works, so that they're anyway doing. However, what's happening now is if you take, you see how urbanization is happening, how new factories are being set up, how new things, infrastructure is coming up. And you have a 2-lane highway, and let's say you make it 4-lane or 6-lane. We take pride in doing that we have now a 6-lane highway connecting Mumbai and Pune, or that has now happening in many parts of the country. So when this happens, when such things happen, a new railway line is laid, let's say between Pune and Nasik, the first thing that is sacrificed is the agricultural land. So that's anyway happening because of many reasons, but even there are man-made reasons why agricultural lands are shrinking. And that is also, we are seeing that there is depletion of the natural resources which are finite in nature, including water and other things. So when we have these constraints, it becomes imperative that the farm yield has to be enhanced. And that's a critical thing to do, because finally, as they say that out of the 3 basic needs of humans, roti comes first. So we have to make sure that somehow the entire population in the world is fed, and that is one of the basic necessities of life. So this, as I said, traditional ways were happening, but over the past 60, 70 years, computers started becoming, invading our lives. And sometime in the decade of late 80s and 90s, that was the time when computers started getting more pervasive in nature. And as they started affecting every walk of life, agriculture could not be left behind. And if you see through the history how computers or computing technologies is being used for agriculture, you will find that the earliest applications included remote sensing and weather prediction. So if you try to see how it happened in India, then the Indian Space Research Organization, the first remote sensing satellite 1A, they launched in 1988, I think sometime in March or so, and within 3 or 4 months it became operational. Thus, we started getting imagery from this satellite, and as we shall see later, this plays a good role in helping how computing can help in agriculture. Then another reason, another thing that plays a big role is HPC. And some of you may be aware that India needed a supercomputer, a Cray supercomputer in sometime in 1985 or 86 for predicting weather, because the first statement itself we said during this lecture that agriculture is playing a big role. So we have to make sure that the farmers get the right weather predictions so that they can decide when to sow, when to reap, when to take adequate precaution. All that depends upon the weather, and for that we needed a supercomputer, which was denied by US, and that's how CDAC was born in 1988 to make a supercomputer. And the first application for that supercomputer was weather forecasting. So predicting weather, not only for agriculture, but there are other aspects like disaster management, etc., associated with it. But agriculture is that the disasters management and all, they are like small, they are things that may occur once in a while, but all through the year, we need this weather prediction for agriculture. So that is how computing started being used for agriculture. So there are not just HPC, as I said, I am definitely going to talk about HPC. But apart from HPC, there are other things that also help in agriculture, those being image analysis, because that's closely associated with the remote sensing that I said. Then the new things, the latest things that are coming up, they include things like Internet of Things, which along with that comes the sensors, and together they help in improving the yield. Another similar thing, small things, the embedded system like things which includes radio frequency identification. Then we are having automation, like many of you would have heard how automation is helping in industry. That is, it is being used for improving the production. It is being used for improving the quality. It is being used for reducing the manual labor. And same thing, like just like automation is helping industry, mechanical industry, it is also helping agriculture industry. Like gone are the days when a farmer would use a pair of bullocks for setting up his field, or those days are over. We came with tractor, and beyond that, tractor was one milestone. But beyond that, multiple other things are coming up. Different types of mechanized, computer controlled mechanized things are coming up, which are helping the farmer in doing the work in a more efficient manner. A side effect of that automation is robotics. And as you are aware that robotics are doing a lot of things today, right from healthcare, they are helping in other aspects in things like firefighting, and in war, and many like mine sweeping, so many other things robots are doing. Similarly, they are being used in agriculture also, and they are helping the farmers in various things, like coupled with let's say image analysis, like they carry a camera and along with IoT. So it's a finally the solution that comes will have multiple facets to it, and some of those I will describe. And I'm sure all of you would have heard about autonomous driving, like Tesla cars, or there are so many other cars, Google car. They are trying to replace the driver with autonomous vehicles. And the problem that they face is that on roads there are men are crossing, another vehicles are in front of you, some vehicles overtake you. So those kind of dynamic things happen on roads, wherein it has to be the radars have to sense them and make sure that the safe driving is done. So now imagine doing that for tractors. Now that's a really good use case, because tractors, you know that they follow a pattern. If they want to move through the field, then they can follow a pattern, so that they go from one end of the field to the other end in a specific way. And there may not be too many hurdles in between. Maybe there are some trees or other things in between, but that can be adequately taken care of. So applying autonomous driving to tractors is one of a good way of making use of computing technologies for agriculture. So out of this, I would be today, due to paucity of time, I will be discussing the first 4 points, and let us begin with high performance computing. So the first, as I mentioned, there are multiple cases, and like CDAC started off with weather prediction as the application. So let's look at that how HPC is useful in weather and climate forecasting, which is indirectly helping the agriculture. So this is, as many of you would be aware, that high performance computing is relates to those kind of technologies that are useful when you want to solve a big problem. And when we say a big problem, it means that we have too much of data or a large amount of data, and that needs to be processed. Then when you talk about HPC, you are also talking about high precision. Like in the morning, my colleague Ashish Ranjan, he talked about the NSM facilities that are being set up, and he would have told you that cumulatively we are targeting at something like 30 to 40 petaflops of cumulative compute power across India. So that's huge amount of compute power. And when we talk about petaflops, we are embedded in that is the floating point operation. Flops in that stands for the floating point operation. So accuracy of what we are doing, precision in that is a key issue or a key attribute when we talk about high performance computing. Other aspect that comes with high performance computing where HPC plays or becomes a necessary thing to use is when you want a time-bound results to be obtained in a time-bound manner. So these three things are very important, that that you have a problem that is big, so big that normal computer that you have a desktop that cannot solve, or the other thing is that it requires large amount of number crunching, and the third thing is that you want the results pretty quickly. So if these are the attributes, then HPC is what is useful, and it uses parallel computing for achieving those targets in terms of solving big problems or solving them quickly. So that is where, as I mentioned, uh, uh, all those use cases, all those problems that needs floating point operations they use HPC. So no wonder that this weather forecasting also uses a model which has evolved over a period of time, and it is still evolving, and it uses some numerical calculations. So here I have mentioned few things which come from the engineering aspects of it, the engineering and the science aspects, like fluid mechanics. Like given the external condition, how does the fluid flow? So when we say fluid, it means liquid as well as gas. So as we know that the air is the earth is a complex system wherein you have land and water, and then further the water appears in all the three forms, that is solid, that is snow covered mountains, then we have liquid, that is water, and water vapor. So all three of them exist, and again this is coupled with other things like how the sun, the moon, the tides, and so many other things that come into picture. So fluid mechanics principles are very much required to take care of this numerical model. Similarly, other thing that plays a big role is the thermodynamic equation. So I'm sure all of us remember the equations that we had, beginning with simple things like P1 V1 upon T1 equal to P2 V2 upon T2. So those kind of equations, those we studied in the school and college, but subsequently we have things like partial differential equations and other complex things that come into picture, which are coupled with time, because this weather changes over a period of time. The boundary conditions, they change over a period of time. So we express them using certain partial differential equations, and we use them, we put a constraints of time as well as the 3D space. That is the entire ecosystem that or the weather system that covers Earth as a sphere, and of course it extends to something like 55 miles or whatever, about after which the Earth starts get the air starts getting thinner. So all these factors on Earth and beyond Earth, they all affect in weather prediction. So we form certain numerical methods, and using those numerical methods, we form a model, and that model will try to integrate all these parameters, and to solve the equation, we give the boundary condition, and this is a complex equations that we need to solve, and at the end of it, we will be able to say that okay, these are the current conditions, these are the dynamic conditions that are happening, that are going to happen over a period of time. So if we start now and try to predict the weather 2 hours from now, 24 hours from now, or maybe 1 month from now, So using these models and giving the initial conditions and the dynamic conditions around, it is possible to say how the temperatures are going to be, how the precipitation is going to be, which area the precipitation is going to be more, and when is it going to rain. So all those kind of advisories can be generated once you solve this equation. Let me also repeat that this is required to be done in a time-bound manner. So that's why we need HPC. Moving ahead, these are the governing equations that I said. That is, you have to apply the conservation of momentum, that is force equal to mass into acceleration. That is Newton's second law, that is applied to the 3D winds that blew across the surface of Earth, and difference of pressure at two places decides how the winds are going to blow and how fast they are going to blow. Then we apply the law of conservation of mass to air and to water. So mass continuity and moisture is respectively are the ones that we are looking at to apply this conservation of mass. Similarly, we also apply the first law of thermodynamics to address the conservation of energy. Like we have to remember the basic principle that the energy cannot be generated, neither can it be destroyed. We can only change from one state to another. Like the kinetic energy of water at a dam can be used for generating electrical energy. So these are various examples that we see in our day-to-day life. They all follow the first law of thermodynamics. Weather prediction also uses the same. And as I mentioned earlier, the gas law, P1 V1 upon T1 equal to P2 V2 upon T2, that is pressure, volume, and temperature. The relationship between these three is given by this law. So using these governing equations, we form a model, and that model is then applied to the data that is collected. So the observations, what we are taking in real time, and the observations that have been made in the past century, together this becomes a huge data, and this becomes the basis for running the model with the data that is available to us. So you have this Doppler radar, then you have these weather stations, then there is imagery coming from satellites. There are specific aircrafts that are deployed in case you are some weather, a storm is approaching or something like that is coming. Then we can collect specific data from a region. Then what are the conditions in the sea, oceans that are collected by the ships which are deployed for this purpose. And there are permanent weather buoys that are stationed at a certain distance from the shoreline. And all this data that comes on a supercomputer. And then, as mentioned in the previous slides, we have those governing equations. Using those equations, we have formed the model. So now these models, like, they are not static in nature, in the sense that they have evolved over a period of time. Then once we predict the weather, we have the facility, or we have the advantage of checking how the weather was, whether how close was it to what we predicted, and in case it was not close, what was the difference, and why that difference came in. Does it need a correction in the model? So that this data that is accumulated over a period of time, that comes very handy. Then further one can apply machine learning, deep learning algorithms to this to arrive at a even better model. So what it means is that the prediction that we are giving today, let us say it is 75% correct. If you use this data and correct the model, it may become maybe even better. So that is the significance of data, and that is the reason why we use HPC, because HPC can work upon large amount of data. Okay, so that was one example where HPC indirectly affects agriculture. More directly, HPC affects which is used for life sciences. That can be very effectively used in agriculture. And in the morning, my colleague Sandeep, he told you how HPC is being used for bioinformatics. I will just try to extend. He was particularly interested in discussing the data aspect of it, how large amount of data is generated and what are the means for taming that data, what are the means of analyzing and drawing conclusions from that data. So I will talk about slightly broader aspect. So HPC has revolutionized the life science, and the first genome sequence, when it was done sometime in early 2000, it was an effort that was made by dozens of labs across the world. They took so many years, and finally they found a sequence and said that, hey, this is the sequence that we have, genome sequence that we have done for a human. At that time, the computational facilities were not all that complex. Over a period of time, like if you look at the history of HPC, you will find that earlier the systems were few teraflops. Okay, so they started with gigaflops, that is 10 raised to 9 floating point operations in a second. They moved over to teraflops, that is 10 raised to 12 operations per second in the early 2000s. In 2010 onwards, we were into the petaflops range, that is 10 raised to 15. And now we are the first exaflop system, that is 1 into 10 to the power 18 floating point operations in a second. That is what it is capable of. That got launched in the June 2022 list of top 500 supercomputers. For the first time, we had a system that could perform one exaflop, that is 1 into 10 raised to 18 floating point operations per second. The top system has crossed that barrier. So point I'm trying to make here is that because we are getting bigger, more and more powerful HPC systems, which are not only can do computationally intensive tasks, they can also work upon big data. They are helping us in doing things in a much easier way, much quickly, and we are able to solve bigger problems. So DNA sequencing is one of the things that now it has become so easy that earlier what used to take days and months, now you can do it in a few hours time, and few GB of data is available to you. And thus one of the applications of this, as all you are aware, for the sequencing of the virus was done. It was done so quickly, and we could find out its variants. And because the sequence was known, we could think of the protein that could dock with it and can be used for making a vaccine. So if that is one, the other thing, there are few more other things which are listed here. Then we can DNAs, they have RNAs, and then they have proteins. So as you go deeper and deeper, the data increases. And if you wish to know their effect, then we need to have more and more compute power. And it is said that even exaflop systems, all the power that is available, that can be very easily consumed by these bioinformatics applications and algorithms. They are looking at beyond that, like after 10 raised to 18, they are looking at a system that can be built in next few years that can go up to 10 raised to 21. So floating point operations in a second. So the point I'm trying to make is that whatever compute power the computing experts can unleash, the bioinformatics and the life science domain is such that it has got problems that can be solved using it. Other ones include protein profiling, which uses high throughput mass spectrography. And then we need, as I mentioned earlier, the protein-protein interactions are required for drug discovery and other such applications. And when external conditions is subjected, how does the whole cell respond? So simulation of that. So these becomes the characterization and analysis of genomic variants. All these things, all these technologies all these methodologies, they become the building block for drug discovery, for finding what kind of what should be the composition of pesticide. So all these things, these are the actual real life applications or the use cases. They are built upon these basic things which are made possible by use of HPC. Okay, so when we apply it for real life situation, okay, so the computational biology is, though it's a field in itself, it cannot work in isolation. Finally, when you talk about computational biology, you have to include things like mathematics, statistics, biology, of course, is there. Then there are biochemical reactions, there are biophysical reactions, and once you have understood them, you have to form a model. The model has to be parallelized because you have to run it on a supercomputer, and then finally you have to apply the computer science to this. And the emphasis, when we use this HPC, we try to emphasize on making use of computers to analyze the data that has been collected using the various methodologies that are described in the previous slide. Okay, and as I've already said, that even a single genome or a proteome, it contains immense quantity of data, and that was one of the reasons why big data analysis or methodologies to store large amount of data has gained importance, and that has got multiple applications. Like you just look at, let's say, take one crop, let's say rice. If you go from Kashmir to Kanyakumari, you will find, I am told that there are about 3,000 varieties of rice itself. Not to talk about wheat, and there are so many other crops. Each one of them have so many varieties. Even mango, like you start with Alfonso mango, which is supposed to be the best from Konkan region, and then there are varieties that are in Karnataka, in Tamil Nadu, then there are in UP. Then you will also find that they do not, those mangoes are not available at the same time. It depends on the one in the south. You get them sometime, I think, in the month of January. The one that we have in Konkan, that comes from April, whereas later than that, in July and right up to August, we get mangoes which are from Uttar Pradesh. So each one of them have got different genomes. Each one of them, they prosper in a different climatic conditions. So just look at the kind of data that all these genomes are going to generate, and then based on that, it can, as I shall tell you later, it can be applied for generating various varieties or improving yield and so many other things. So this genome scale data is huge, and that's the reason why we need large scale computations. The HPC becomes a fit case for that. And as was told in the first lecture today, that you need appropriate database system. Then visualization is other aspect that even the teams at CDAC are working on, and the docking and other things, they can be very easily visualized using, now we get 3D TVs and 3D projection systems. They can be very easily used. Okay, so that is about computational biology. So I gave two examples of how HPC can be applied for weather and computational biology, and they in turn are going to form the basis for application into agriculture. Another kind of vertical which can be used for agriculture is image analysis. So first we will see what is image analysis, and like we all know, we know remote sensed image, we even know these principles, they apply to any image, like they apply to face recognition, they apply to crop pattern recognition. So all of these, the basic mathematics or the basic computational aspects behind any kind of image is same. So what does the computer do? It converts it into a number matrix. So if you take a black and white image, every pixel can have a value 1 or 0. But if you take RGB image, if you have 1 byte per or 8 bits per pixel, then you need 24 bits for each pixel, because a color pixel consists of expressed through three basic colors: red, green, and blue. So so each element in the matrix is a pixel. And then once that is done, what can be done with this? You can do image enhancements for better clarity. In case images are sometimes they get distorted because of some disturbance, especially when you are taking a remote sensed image, cloud cover, or changes in the atmospheric temperatures, they distort the images. And as a result, you need to restore them for better processing. Then when you want to transmit these images, you need to compress them because raw images are very heavy in size. And finally, you need to do image analysis. So what is that the image analysis does? So image analysis allows us to take or pick up specific information from an image. So three examples are given here. You can look at the edge of an image. So like there is a background and there is an object of interest in that image. So how do you pick up the image, the object of interest? By removing the background. So you look at the edges which forms the boundary for the image. So you are extracting the image. That's the first thing you do. Or there could be some pattern that you see. Let's say you can imagine a crop pattern with rows and rows of, let's say, rice plant, and let's say somewhere in between there is a tree. So that tree is forming canopy on the field, and then you want to figure out which is the area which is getting affected. So how can you do that? By looking at the color. So texture analysis, so you'll find a repetitive pattern in the crop, and that will change if there is a tree in between. Or you can take images over a period of time, and you see what are the movements. When you say movement, we can say changes. So this movement that I mentioned here, that could be applicable to if you are taking successive images from a video, okay, for let's say to see how a car is moving. But in this context of agriculture, it could be the movement could be over a period of time, that let's say this is a time to sow rice, and then the plant grows and the rice starts maturing, and then you see over every day you take an image and you will notice the difference. And a point will come when you can figure out that okay, this is the time now to reap it, cut the plants and take rice out of it. So that can be done by comparison, that is changes between one image to other. And what is the science behind it? It starts with image acquisition, like either remote sensing or a machine vision image. Then you pre-process it, that is the image is optimized. You take out elements of your interest, do the pre-processing. Then if the image is large, which is normally going to be the case for an HPC kind of application, we have to do a segmentation. Segmentation is also useful because in HPC we need to do parallel processing, and there are multiple elements available to us. So instead of doing it serially, you just segment it, and the same algorithm can be applied to every segment. And once the entire segmented image is assembled together and the data extracted is put together, that's how you can interpret it and decide how that image, the analysis that is done is to be used. So that's the interpretation part. So now let us see how does the remote sensed images are used in agriculture. Okay. So now the way it works is during the daytime, the sun gives us light, which gets reflected from the crop. Let's say that's what we are looking at, and that is captured. Now the advantage of having it in the sky is that you get a large you can get a large area covered in one shot that you take. And then once the data is collected, it is transmitted back through communication channels to the dish antenna. It is received by the earth stations, and then you do the computation on it. So now let us say in this case, what's happening is that you can tell the agriculturist that okay, this is the time you can go and cut your crop. So that kind of decision making is possible through the analysis of the image that you captured through remote sensing. So this is one example that I gave, but things have progressed so much that you can apply algorithms, and looking at the images, one can tell if there are any nutrient deficiencies. As indicated, I am not an expert in this field, but possibly due to the color of the crop and how a good crop looks like, and how a nutrient deficient crop, how does it, what color does it have. So these kind of things, or a fungus, if a fungus is affecting the uh, uh, leaves, then that can be very easily detected. So these are the some techniques that are available to us that can tell us immediately about such things. Or if you look at the soil, take the crop is on the soil, so you have a pattern of soil and crop. Now looking at the color of the soil, one can tell whether it has a deficiency in water or water is surplus. So that information can be given to the farmer to take corrective action. Or if some weeds have infested the crop, which is not a good thing, so that they can be removed. Then if there are multiple plants in a given area, what is their count, or what area are they covering? Similarly, so that is a normal that can be used during a normal time. But sometimes there are some adverse conditions, like locusts, they come and start eating your crops, or there are other insects that come and they land on the crop. So generating alerts for that can be done if you can, if we can figure out how the pattern of insects when they are sitting on the crop look like. Or there was a hailstorm, how much damage has been caused by it. Or after the insects they struck and they went away, how much crop was destroyed. Or there was strong winds, or there was some kind of cyclone kind of thing, how much crop get affected. So that can be done through this, and that helps the government to give compensation and take appropriate decisions. Another thing where images are used is what is called as machine vision. So this machine vision can be used by robots. Now robots itself, they can do a lot of things, but when they are equipped with the machine vision, so like suppose they are in an orchard of apples, and you just program the robo and let it go through the orchids, because your trees are in a particular pattern, so it can go between them. Then it can look at things like, by taking the image, one can say, like looking at the color and the texture of the surface of an apple, one can say, is it time to harvest it? Or if looking at the soil, it can say, is it a good time to plant or remove the weeds? Or make a map in your field as to which part of your field has got what category of crops. Okay. Then another type I am told is like, another thing that it does is what is called as phenotyping. So this can identify the best breeds. If you have a mix of breeds in your field, then you can monitor its growth over a period of time through machine vision that is collected over a period of time, and then identify the ones that are good. Then this is also very easy to do, that grading and sorting. So you have some crop that has matured fast, some crop that has not, and you know that some of it is good and some of it is not good. So you can classify it, the farmer can classify it and say that which one of them is good for longer shipments, and which one needs immediate attention and can be sold in the local market. Agriculture also comes with livestock, and one can look at, suppose there are sheep, or the farmer has got cows, then it can be used for monitoring their growth, and then that can be used as advisory for veterinary doctor or something like that. Then finally, I talked about autonomous tractors. So for moving them, they need machine guidance. There is a machine vision, and it can identify if there are any things that are coming in its path. and then appropriately guide the tractor. Okay. Another thing that is coming up is called as Internet of Things, which is becoming a hot topic as applied to agriculture, and I'll show one case study of that. So what is Internet of Things? It's an is a network of physical objects, or what we call as things. That's how that IoT. Things are nothing but objects. Now these objects carry with them sensors. Some of them carry compute power. They are battery powered, and some software, which like they will typically have a wireless port through which it can offer connectivity. Over this port, it can send data. It can send data to a server, or it can send data to its neighbor, and that can be extended once the network is formed. You can give network internet connectivity, and finally data can go on the cloud. Okay. So what is there that is used by IoTs? One is the low power sensor technology, like humidity, temperature, and many other parameters can be sensed by this using very low power sensors. Then the next thing that it needs, because it cannot keep the data itself, it has gathered the data. What is to be done with it? That data needs to be sent over network. So typically they use networking protocols that allow them to communicate with their neighbor. And the protocols are such that they do not consume more power, because wireless essentially, as you would know, that like if you are using mobile phone, within a day or two the battery drains off, because when it is communicating over wirelessly, it is consuming a lot of power. Where does this data go that it is sending? Typically it will go to a cloud computing platform, because you can, if you can scale it up well, and there is somebody else who is managing it, so the life of the person who is using it becomes simpler. And finally, what do you do with the data that is collected? You do machine learning and analytics, and that is very important, because you have vast data and you use AI and machine learning techniques, and that can give you as to quickly data can be analyzed, and certain actions can be suggested, as we shall see in the next slide. All these techniques that I mentioned, they can be used for things like precision farming. So this is precision farming, as you know, that you make accurate use of in a controlled environment, so that suppose the plant needs there is a cloud, and because of which humidity is already high, and as a result, uh, as compared to a sunny day, the water from the ground is not evaporating as fast. If you know that, then you can give just adequate amount of water. That improves the efficiency, and as the name suggests, you are doing accurately in a controlled manner, and you are using the resources efficiently. Then these days, a new thing that is coming up uh, in the field of IoT, and which is coupled with drones, is they are used for health assessment, monitoring. Sometimes they are used for spraying pesticides also, and analyzing the field as to taking the overall view of the field. And they are using specialized cameras which can capture multispectral images, they can capture thermal images, and they can also capture visually. Appropriate image processing techniques are used subsequently. Greenhouse, many of you would be aware, and they are like a controlled environment. And when you are controlling the environment, you need to make it precise, and you don't want manual intervention in that, and you want it to be happening automatically. And the sensors, along with the control mechanism, can maintain the humidity, temperature, and other parameters which are good for the crop that you have put in, or the plants that you have put in, to prosper. Like one of the good examples of this is like in places near Pune, they are using to grow roses, which all of them are exported. Then while this is being done in a small scale, if you want to do on a large scale, like you have spread over acres of field, you need to monitor the climatic conditions, you need to put the sensors across the field and collect real-time weather conditions, and that can be fed, like I had mentioned to you, for weather forecasting and other things it can be used. And finally, the animals, they can be tracked and made sure that they do not leave a pre-designated area where they are grazing, and that is called as geofencing. Similarly, other things like there are health and other things can also be monitored. And another technique that is being used is called as RFID. So I'm sure many of you may be using a credit card or a debit card that has got a chip built inside it, and you must have seen that up to 2000 rupees you can tap and pay. So without inserting the card, how is it reading? That is because it's a contactless method that is being used. So same thing applies here. There is what is shown on the right hand side top is a tag. It can come in various forms, and those tags they store the information, or they also have sensors, some of them, and they do not have any battery. Some of them have battery, and you just need a reader, the black thing that you see here. uh, Even when the thing is passing by, something, there's a movement, still they can read. So there is an interrogator which collects it, and of course that sends it wirelessly to, or through a wide medium, to a central computer, where the received data is managed, and it can also tell which readers to work, which readers not to work, and enabling them. All that can be done in a centralized location. So how can it be used in agriculture? One is that it can track the life cycle of a plant. So you attach such tags with it, and when you are doing experiments, you can see how it has happened, and then link it to the properties of the output. Like you have a tomato plant, and you see what weather conditions it was subjected to, that particular plant, and collect that data in the RFID. Keep reading it once in a day, and then you can then look at the yield subsequently in a month or so, and then link it to how you got it, and whether it was good or whether it needs improvement, that kind of things. Similarly, tags are also put on apples. They monitor the gases, and then they will tell that, okay, this is a good time to pluck the apples. If the food is sent, or the roses or flowers, they are sent over thousands of kilometers, then they can be monitored, whether they were in good condition, whether there were the climatic conditions were good. So all that can be done, and these what these RFIDs allow us is micro level monitoring. Like they can be very small in size. You can connect it to even a fruit, or you can connect it to a plant, and you can monitor things like light level, humidity, soil chemistry, and then link it to the yield you got. So I will just finish off with two case studies. I have 10 minutes left. We'll have some time for questions also. First case study is one that our Hyderabad center did, which is called as Harit Priya. So they used IoT based techniques for precision agriculture farming and agro advisories. So what it does is I will show the pictures later. They developed an IoT node with a sensor with temperature, relative humidity, soil moisture, leaf wetness. All these things were monitored by every node. These nodes communicated with a gateway, and the gateway also had certain sensors like rainfall, solar radiation, wind speed, direction. All that was measured by the gateway. And finally, all of this was connected together and sent to a cloud. And there was a decision support engine for telling whether there are any pests that are attacking, or a disease forewarning, or when should it be watered. All those things were advised, and they were sent in local languages. So this is how it used. So you have multiple nodes, wireless sensor nodes spread across the field, and then they communicate with each other, and through a gateway they send it to the cloud, and then you have a computing infrastructure that interprets it. So this was done for government of Andhra Pradesh, and it provided advisories in local language, and about 450 acres of land was covered, and 750 farmers were making use of this. They're still making use of it, and then I think they have transferred the technology, which somebody else is now implementing. Okay, so this is how it looks like. They used it for groundnut, and you can see here, I'm not an expert in this, but it shows how the things were monitored on the leaves. And ICRISAT, which is in Hyderabad, and CRIDA of ICAR, these were the agencies that provided the domain expertise to this team. And this is how it looks like physically, that this is a gateway node, and you will have many such nodes that are collecting data. and it also has some control which tells how much to water and all other details. And as I mentioned, these messages were sent, and the users, they subscribed, they told what is their geolocation and all, and based on that, advisories were given in Telugu language to each farmer who were one of those 750 farmers. Okay. Another thing that which our team at CDAC Pune has used for agri advisory. So they had a mechanism by which they collected the data. I already told you how the data is collected from radars and other things, and that data was collected, and this was done, I think, for state of Jharkhand. So this data was collected and it was used for there were two things that they told, as you can see here. One is for giving advisory for how the monsoon is going to be in short term and long term. And based on that, there was an advisory that was given about the agricultural aspects. So they had mobile based app based on which one could collect. I mean, one can gather the information, and it was given the what district, what block, what panchayat, and it was given in you could also select the language also. I think I have not shown it in Hindi, but all these details were given to the farmers. Got a different view, and the users who are from the department of weather forecasting, they got much more detailed views, which in turn, and they could then advise the farmers. So it was given as, okay, yeah, they could give it in the local language as well, and how frequently you want, and other parameters could be configured. Okay, so they made this general advisory preparation, and as the whole project, it involved one could select the crop, like what they have grown, rice, maize, the list is here, and the information was given in English, Hindi, and Nagpuri languages, which are the ones. So the decision support system, there were 10 areas of interest that were designed, like what to sow, when to sow, how much fertilizer to put, if there is a disease, how to manage it. So it was more like you can say an expert system that was advising farmers in a real time. So that brings us to the end of my talk, wherein what we saw in the past 1 hour. We know that HPC and ICT technologies are being made use of in every walk of life, and agriculture is no different. So it can go from large scale level like weather to micro scale level like cell. So I mean, you have to just decide where is that you want to apply it, then go at the root science of that, how the science handles it, then create models for it, and use HPC to run those models and arrive at a decisions or interpretation or analysis. And now it has becoming more and more crucial, as I said in my opening remarks, because food security is an issue. Like I'm sure many of you would have known that India had put a ban on wheat export. There was a scarcity of wheat in the world because of the Ukraine Russia war, and that is something man-made. But there are other natural calamities that also create food security problem, and that has become a priority for every country. Just like water is priority for every country, and similarly food is also a priority for every country. And India, it becomes all the more important because we know how big our population is, how fast it is growing, and we have to feed every citizen in this country. So for the those who are the planners, those who are doing the planning, for them, this becomes a very, very important tool for how to make sure that our future is secure. So that is all I have for today. I think I maintained time. Yes, we have some time, 5 minutes for Q&A, and I would be ready to take any questions that you
Thank you,
have.
Mr. Ashish, for giving a wonderful talk and giving the key insights in various case studies being used in the agriculture domain. Thank you so much. Participants, any question, please?
It was A very interesting talk, and you have covered almost all the areas of agriculture, from genomics to precision agriculture and IoT. So you have very well covered the talk. So everything looks very interesting, and we would be very happy to collaborate in these areas. Thank you very
Yeah,
much.
sure.
And it is difficult to get so many application of SPC in one presentation. So this was a great.
I hope it was not information overload.
No, not sir, not really, because we if we try to find the application of SPC, merely we get 1 and 2 or 3 application, but you have elaborated many applications. That's great, sir.
Thank you.
In fact, we got pointers with your discussion, and people listening here, many of the students working in this area, postgraduate students, some undergraduate students are also connected under BTP. So
Okay.
they are going to use HPCs. It's not only the postdoctoral fellow or research associate in the project who are working with supercomputers. Our undergrad students also, we formed the team and they are using supercomputers with
Very good.
genome sequencing problems. So they are listening your talk. However, it's not visible here, but it is through YouTube they are connected.
Okay.
And, definitely they are getting the pointers. In case of anything, we'll approach to you. We are in touch with you.
Yeah, sure. They can also note down the email address which is on the screen,
Yeah.
and they can give reference to this workshop so that I can put the query in the right perspective.
Yeah, Preeti and Rajesh, I am hoping you are noting down students group working with us, no? Undergrad students.
Rajesh, can you post some queries on if it is available in the YouTube for this session?
Any queries on YouTube?
As of now, there is no query.
All right. Doesn't matter.
The question was so elaborated, so nobody has doubt because there are many applications as discussed.
Okay, thanks, Mr. Ashish.
Yeah, thank you very much.
Thank you very much.
Yeah. I will stop sharing the screen and
So now I would request Dr. Preeti to kindly introduce Dr. Milendra Ratnaparkhi.
Good afternoon, everyone. Next talk is delivered by Dr. Milind Ratnaparkhi. He is a principal scientist biotechnology at ICR, Indian Institute of Soybean Research, Indore. He has over 30 years of experience in the field of plant genomics, genetics, and biotechnology. His current research involves comparative and functional genomic studies to identify genes for important traits and in the development of new computational and bioinformatics tools for the analysis of plant genomes. He has published more than 40 journal papers. He is currently the principal investigator of a major research project funded by ICAR National Agricultural Science Funds, Science and Engineering Board, CSIR, and many more. Over to you, sir.
Thank you very much, Preeti, for the introduction. And good afternoon to everyone. It's great pleasure to be here. Since yesterday, we have heard excellent talks on the application of high performance computing in agriculture and genomics. So was very interesting. I will discuss about the work, what we are doing, and what are the challenges we are facing, and how HPC can be applied in for solving the problems of agriculture. Yeah. So the what major challenges that everyone has discussed that what we have seen is that the weather is getting unpredictable, and sometimes if we consider the rainfall, there is a continuous rainfall or there is a dry spell. So there are climatic conditions are changing, and for crops to adopt these climatic conditions is difficult. So therefore, there is a need to improve these crops so that they can adopt for all these different climatic conditions. The biggest stress about what the agriculture is facing is about the abiotic stresses, drought, and also the water logging. So these are the very important stresses, and all over the India, different crops face these stresses. Similarly, biotic stresses are there. A lot of new diseases also we are observing, and it is important to identify the genes for different diseases and then to improve the varieties so that we can make the plants resistant for various diseases and insects and pests. Besides this, there are other challenges also, and increasing the yield is the biggest challenge. What we have found is that for several crops, although the yield have increased, but for some of the different crops, the yield are stagnant for several decades. So this is a big challenge to improve the yield of major crops. And the nutrition quality is also very important. In India, we know that malnutrition is a very big issue, and the protein is needed, and a lot of nutrients are needed for the population. So nutrition quality is very important, and similarly the oil quality, oil content, these all can be improved using the genomics approaches. And for genomics, we need to identify genes for all these traits, and then transfer it into the varieties which farmers are growing. As I'm working on soybean, this is a very important oilseed crop. And in India, we are not self-sufficient in oilseed production. More than 60 to 70% edible oil is imported from other countries, and we have to spend a huge amount of foreign exchange in importing the edible oil. So currently, the Indian government is stressing a lot for improving the oilseed crops, and here again the genomics and HPC can be a very useful. I will discuss about how we are doing the analysis. So first I will discuss about the phenotypic analysis of plants. And this is very important. If you want to identify any gene, we have to extensively characterize plants for various phenotypic traits. And in each institute, we have thousands of lines are available. For example, if we take rice or wheat, thousands of different accessions of rice are available. And we have to screen all those thousands of lines and identify those lines which are very crucial. So here in this photograph, you can see there is a one control field, and another is the field where we have given the drought stress. We have stopped the water, and like this, we screen hundreds of lines and apply water stress at a particular stage. So in these crops, some stages are very important, like the flowering stage or when the seed is forming. At that time, we stop the irrigation, we stop the rainfall, cover these fields, and then we measure a large number of parameters which are associated with the drought. And on the other side, on the control, it is fully irrigated, so we can see the differences. And then when we use these plants for our analysis, for phenotypic analysis, for genome identification, so we take the leaf from both the plants, control and drought, and use it for DNA extractions, RNA extractions, for identification of proteins, which will be very important to identify which protein is crucial for giving the drought stress. So this phenotypic analysis, lot of importance is being given. Recently, high throughput phenotypic approaches are available, and very accurate data is generated. Here just I have given some example of drought. If after the giving this stress, there are large number of parameters we measure. First, you can see the seed yield from all those thousands of lines we measure and see which line is giving good yield after giving the drought stress. Similarly, the seed weight is there, then biomass, then the plant height, the number of pods, number of nodes. So we have hundreds of different parameters even for single traits, and all these traits are very crucial. So if we want to identify a gene for drought, it is not a single gene which if we identify it will give tolerance to the drought stress, but there are complex, a large number of genes which are working together, and they provide resistance to the plant for drought tolerance. So all these traits related to drought may have different genes. Some of the like seed yield is a very complex. It involves a large number of genes. So we have to identify genes for all these different parameters, and then bring all these genes together in a single variety which the farmers are growing.
So therefore, developing the variety is very complex for these traits for drought tolerance. And here lies the major challenge to identify the gene and to identify the regions where these genes are located and some markers which will be very helpful in the breeding program. Next, there is another trait which I want to discuss. Like these are some of the lines which we have identified after giving the stress and even giving stress of around 15 to 20 days of drought stress without water, the plants are still green and leaves are green. So like this, we identify the unique lines and these lines are then passed over to the breeders and they cross this, take these lines, cross with the other varieties which is farmers are growing, and then transfer this trait to the varieties which farmers are growing. So this entire process of identification of genes, then identification of the plants, and then developing varieties is very long. It can take several years, up to 8 to 10 years are there minimum. And using new approaches, we can shorten these period and develop new varieties. This is also uh, another area which we are working is on water logging. This is also very important because we have seen in certain states there is continuous rainfall, and if the continuous rain for 10 days or 15 days, the plants are under water stress condition, and farmers will not get any yield. So what we do here is there is a large field and we fill this with water and maintain this field continuously for around 10 to 12 days. So this stress is given to the plants and then after that important plants are identified which is able to survive, which has given a good yield. Then again hundreds of parameters, phenotypic traits are measured. This may include like chlorophyll content and photosynthetic rate of these plants. And again, the sophisticated instruments are used for measuring all these traits. So after giving these traits, different phenotypic data is measured. So at the bottom, you can see there is a foliar leaf damage score. And this we can easily observe that some of the plants are becoming yellow, very few leaves, and some of the plants are green. So this, after giving this test, these are identified. And on the roots also, we can clearly see the differences from the lines which are resistant to waterlogging. So these lines are also identified. Then a lot of parameters are scored and the top genotypes which are giving good yield are identified and they are further characterized. And later we go for molecular studies to isolate the RNA for gene expression and also genome sequencing to identify the gene for waterlogging tolerance. And the next state I would like to discuss is the root system architecture. This is a very important for drought. And here what we do is that there are long pipes, 5 to 6 feet long pipes, and these are already cut from half. And then we fill these pots with the soil and the plants are there. So after they mature, we open the pipes and then remove the roots from all these plants and then see what is the root system architecture, what is their length, what is their density. So this is a very laborious work and this phenotyping of all these traits is very important if we really want to improve these crops. This is the variation in root trait architecture. So here we can see some of the plants have very small roots while some of them have very long ones. And also we measure different angles are there. So we have to identify if the angle, which type of plant is better for drought stress, for waterlogging. So all these parameters are measured and used for our phenotypic studies. These are some of the traits for root system architecture like root depth, length, then density, surface volume, then root thickness. Then we do have a scanner And this scanner is used for observing various traits. So all these routes are scanned, and we get additional data like number of forks, number of crossings. So it's a very extensive study and very laborious. And what is observed that this timing is very important. Like if we are delayed in taking the readings, then the route gets degenerated. So very timely phenotyping has to be done for all these traits. Now I will discuss about the molecular approaches for gene identification. So once the phenotyping is done, there are three major approaches which we are following. One is genome-wide association study, then the comparative genomics and functional genomics studies. So all these three approaches we are combining together to identify the genes, to identify the markers, which the breeders can use for further studies. Here I would like to show one picture, and this is a functional genomic studies approach what we have done. So here what we have used a technology to overexpress the RNA which is present in plant. We used biotechnological approaches and again increase the quantity of the RNA. And what was surprising is that after increasing the RNA level, the plant became tolerant to drought and salinity. So this is one approach to where we can overexpress the gene and also make the plants resistant for drought or disease or other traits. So these technologies are now standardized in our laboratory and in collaboration with another laboratory in Maharashtra. So we are very excited about this. But before this, we have used all the approaches, comparative genomic studies to identify the gene, and that single gene was identified and then overexpressed. Another technology what we are using is gene silencing, and here again the RNA is blocked. So if a particular RNA is blocked, then we want to observe what is happening to the plants. And again, we found that after blocking the RNA, the plants are becoming tolerant to drought and other stresses. So these are very important technologies. And once the gene is identified, we can demonstrate it into the plant and see that what is the phenotype, and this will be helpful for developing the new varieties which are tolerant for drought and various traits. Now I'll discuss about some of the plant diseases, and for all the crops, a lot of diseases are there, and we have to find the genes again for all these diseases. At our institute, we are working on several important diseases like anthracnose, charcoal rot, rust, and these are located in different states, like they appear in different states of countries. So for that, we are identifying genes. And the strategy what we are using is again like genotyping by sequencing, whole genome sequencing, and functional genomics or phenomics approach. So recently we conducted whole genome sequencing of a line that is rust resistant, and this occurs, this disease occurs in Maharashtra, southern Maharashtra and Karnataka region. So only one line was found resistant, and that was used for whole genome sequencing. And this sequencing data we got on all the chromosomes, we were able to identify the differences, which we call as single nucleotide polymorphisms, SNP. And this graph is showing that on 20 chromosomes of soybean, how these SNPs are distributed. And then we use various computational tools to identify the genes. So in soybean, worldwide, lot of genome sequencing going on. In US, if we see more than 1,000 to 2,000 lines have been sequenced, so huge data available in this lagging crop. And we need to use large-scale computational tools to compare all the whole genome sequences and to identify the genes. This is the area what we are working, and SNP clustering is very important, not only for plants, but in any organism. This approach is important for identification of genes and also for identification of the markers. And in collaboration with IIT Indore, we are working on developing new algorithms for SNP clustering. So this is the chromosome where we have identified the disease-resistant gene, and like in this crop, soybean, 40,000 genes are there, and the function of very few genes is known. The very few percentage of genes are known. So there is a huge scope to identify all the new genes, where they are located on the chromosome and what is their function. So after identifying the genes, what we found is that on the chromosome 18, there are three genes which are very similar to each other, and these genes, the sequence data of these genes was compared, and they all perform the same function. So we are still working on these genes. Like out of these three genes, which gene is the most crucial, which provides the rest resistance. In addition, as I mentioned, like in soybean, 40,000 proteins are there. So there is a big scope to do computation analysis of these proteins. So we use various bioinformatics softwares to cluster these proteins. And if these proteins group together, they may have similar functions, although some proteins may have diverse functions. So this is very important area, and a lot of work going on in genome-wide analysis of gene family. This is a picture where we have analyzed the families from different crop species, and after grouping them together, we can identify from in different crops that which genes are very closely related, and we can use the information which is available from different crops for crop improvement. Similarly, gene structure and gene location where they are located. So all these information we generate through different bioinformatic tools, and this is necessary for finding the location of these genes, on which chromosome it is present, then what is the protein structure, what is the conserved domain. So all these informations are necessary in plant genomics research. As I discussed that right now a lot of plant genomes are being sequenced, and the data what will be available will be in a huge data. So we need a lot of new tools for the analysis of these plant genomic data. If we look at the wheat genome, the genome size is very big and complex, and it has a lot of elements which we call as mobile elements, transferable elements. So they make the plant genome very complex, and new algorithms are needed to identify these mobile elements or to identify the location of some genes. So some new tools which we have worked, I'll just discuss. This was some work on identification of gene synteny, and this has been used for public plant species available. And through this bioinformatic tool, we can compare different plant chromosomes on different crops and identify the gene locations. This is just an overview of the work, and different programs are combined together, including BLAST-P, then MC-Scan program, and then finally we get an image which gives a very clear information about the different chromosomes and the genes which are conserved. This is the work what we are doing in collaboration with the group, Dr. Tiwari's group, and I'm very happy that last 5-6 years, a lot of new computation tools have been developed for clustering of SNP sequences, for clustering proteins, and for clustering DNA sequences. Work is going on for clustering of RNA also, and we are hopeful that soon we'll be able to combine these tools for analysis of plant genomes. So in summary, I would conclude that a lot of huge genome data is available, and comparative and functional genomic study is very crucial for plant, and we need a lot of bioinformatics tools which can analyze this data, identify the genes, identify the markers, and these markers we can provide to the breeders who can develop the new varieties for different crops. So with this, I thank you very much, and I'll be happy to take any questions.
Thank you, sir, for informative talk, and definitely it will be helpful for the new study of phenotypic level. We have already done the genotypic studies. Now we'll proceed with the phenotypic one. So thanks for a good talk. And participants, anyone have any questions, please raise.
Rajesh, any questions from YouTube?
I have a question for
Yeah.
Dr. Ratnavar. So, for drought tolerance and submergence, which genes you are overexpressing in soybean?
Yeah, that is a very important question. And so for drought tolerance, what we found is there was a fat gene which is responsible for oil quality in the soybean. And we overexpress this fat gene. And after overexpressing it, it showed the tolerance to the drought. So that was a very new information, like the gene which is also playing important role in seed composition, oil quality, and that is giving resistance to these in soybean for drought tolerance. But in addition, we had previously looked at the Arabidopsis, and we have taken some of the genes from Arabidopsis also. So DREP gene family is there, and FNSL gene family. So we have selected orthologs from different crop species, which are known for providing resistance for drought. And currently, we have used those to suppress the gene or to overexpress. But the genome-wide study is going on, and we are waiting for the sequence data, GBS data. So once that is available, we are going to do Jiva studies to identify the genes from soybean itself. And those genes will be again doing functional genomic studies by RNAi and different approaches to confirm the function of these genes.
Just one general question. As a plant scientist, so means whether this strategy means if we introduce those alleles, means orthologs from, for example, tolerant legumes like khejri growing in the desert, which are not so yield effective, but they are designed to survive. So do you think this strategy of introducing these orthologs from other species is more suitable, or just we want to overexpress the internal genes in different genotypes of the same species, soybean?
Yes, that's a very important point. And yes, I think if in any other crop the gene is available, which is giving a very high resist tolerance for drought or for disease, it can be taken and it can be used for providing the resistance. That is a good strategy. And of course, because if we look at the insect in soybean or any crops, genes are not available for the resistance for insect. So we have to take their genes from other crop only to and introduce them for insect resistance. For drought also or other trait, if the gene is available, that is possible. But only we have to look at the acceptability of the transgenic plant if we introduce the new gene. If we modify the gene within the same crop using genome editing, so that is more feasible right now, as genome editing has been widely used for modification of these genes. So I think both the strategies are fine depending on its application on different crops and its role in the trait.
Thank you.
Any other questions? So, however, I am in continuous touch with Dr. Ratnaparki since years. Still in this half an hour time, I found many number of problems, more problems, which we can do, Dr. Ratnaparki, like phenotypic thing we haven't touched till now.
Yeah.
So, precision agriculture and so many things he was talking. So still many things are to be done for over the years. It's not a short period of time, a long-term plan we can do, go ahead with more high performance computing.
Definitely.
Yeah, Amit, any questions, please? Any comments?
Yeah, I think Dr. Ratnaparki's experience is guiding us for our Bharat Agri-Grid. And I think that project, that soybean that we have done, is a proof of concept that we can take further, and we can implement it on the Bharat Agri-Grid. And this is going to be a very big level, a large level at the country level. But the proof of concept that I think IIT Indore has taken with Dr. Ratnaparki will definitely going to help, and we are going to have more and more learnings and with now IIT Jodhpur also involved. So we will really get more learnings, and then we will use it and try to improve our system as we go further.
Thanks, Amit. We are definitely looking forward to collaboration with everyone, and we can progress only the expertise of all of us is combined together.
Yeah. So any more questions from anyone? So we are about to end the session. Amit already has given the remarks for this workshop. Any more comments about the workshop, Amit? Then I'll move to other people.
Yes. So I think the this is a second phase of our workshop. I think with 2021 we started with our first phase of the workshop. Now this is the second. Now we can see the changes. Like that time we were uh, trying to see general. Now we are trying more specifically about Bharat Agri-Grid. And this time we have a very clear-cut panel where we discussed exactly what we are going to do, and what is expected by the country, and what is expected, how we can help the various breeders. So this is now we are moving more towards the goals that we want to achieve. We may not be able to give solutions to each and every problem of the farmers, but we can try that indirectly. Can we help farmers through the breeders? If even we help the breeders, even we help the ICAR institutes, then also this is a great achievement. We can see that we are building a lot of supercomputers, but we are building all these supercomputers. That is one of the questions. The supercomputer is there to solve some problems. Now that problem should have some societal impact, and when we see agriculture is really area, and where the societal impact is really most visible. So when we if we are able to solve at least some of the problems by using supercomputing power, uh, like developing a special traits, even the genomics, and like when we say genotypic and phenotypic things, even as I think the Professor Anil Rai was saying that a lot of data has to be analyzed. Now, this analysis has to be done by the computer engineers, and this analysis uh, can show us a way that how further the crops can be improved. So this data, so we like yesterday also that we have to start with the data. So the data is very important part, how the data is to be collected, how the data has to be filtered, and how the data has to be in such a form that it can be consumed by our AI pipelines. Now, when we say AI pipelines and this machine learning engines, those engines has to be trained with very specific data requirements, and from there we come out with some type of means analysis or results that can show us that, yeah, if we try to do this type of gene is really more means like it's a it's it is more helpful in developing this type of crop, and this type of gene is over expressing more, or so that this type of scenario, if we are answering through our analysis pipelines over the huge computation power of the supercomputer, so then definitely I think this can solve in a future a lot of problems that the breeders are facing, that the ICR institutes are seeing. We can see that already IASRI has this Ashoka grid, but the data is huge, so now they are not able to meet up the requirement of all the people. Right. So the requirement is huge. So now how we are able to cope up the requirement of this community, that we have to see. Now this Bharat Agri-Grid, if it provides a virtual platform which connects all the stakeholders together, and which provide the analytic pipelines, and which provide a very useful portal where everything can be accessed at a single entry, and we can get an overview. So if we are able to make this type of infrastructure available through this virtual pipelines as well as this portal, then definitely this can be really, and this can only be done when we collaborate together, when we work together. So this collaboration is a power where computer scientists, HPC, NSM supercomputers, cloud, grid, and genomics, and everything comes together,
Yeah.
and we try to solve a grand challenging problem. So that is what I want to say. Thank you.
Yes, since morning I am observing there are so much infrastructure available, as CDEC mentioned, all three eminent persons discussing in their talks, NSM infrastructure, the computing power, like Sandeep Malvi discussed about the computing power, storage power, the NSM details by Ashish Ranjan, Ashish Pulvekar sir mentioning about the case studies which are really happening in various regions of the country with IoT and specialized kind of infrastructure. Infrastructure is there, but the need is to come all these scientists all together, like computer scientists, the agriculture scientists, the HPC people who are working in CDAC, and obviously the stakeholders, the ground persons. We must come to know the needs, and then only we are able to solve it. So this time in this workshop, it's a good thing that more institutes are collaborating and working with a specific problem. Like Dr. Karthikeyan is also joined just now. He's a very experienced person, uh, like guiding us in a collaborative manner and how to go ahead and find out the track so that you can reach or you can meet the stakeholders' needs. So now I request Dr. Karthikeyan, please share a few words for this workshop. Dr. Karthikeyan, I am audible? I think he is having some connection issue. So let's proceed with Neha. Please share your views for this workshop.
Thank you, Dr. Tiwari. So it has been nearly 8-9 years for me to working with Dr. Tiwari as well as Dr. Milind Ratnbargi. As I've started my PhD, it was a long journey that designing machine learning algorithms and working with these algorithms is you can say a go-on thing for the AI person. But finding a society application where you can benefit the society is a great thing that you can contribute, going to be a great contribution by an AI expert, if you can say. So without Dr. Ratnaparki, things would not be possible in that manner, because he's the person who have guided us in to work with this application and designing the algorithms for the agriculture sector. And since then, it's a long journey we have covered. And right now, I would say I have learned a lot from him, especially in this domain where I have not at all an idea. And sometimes it gives me you can say a fair kind of thing that how we will scale in this agriculture domain, because we are belong to a computer science domain. So it's really a pleasure working with you. And now we have a huge team. So Mr. Amit has joined, even Dr. Karthikeyan has joined us, and Dr. Ayan from IIT Jodhpur has joined us. And we are hoping that we will come up with more agriculture solutions so that we can benefit our country and can come up with Bharat Agri-Grid. Okay, so that it could be a you can say a designated platform where we will be thinking of deploying our algorithms within a pipeline structure, so that even though the person who is not very proficient in the computer science domain or in the agriculture domain, but want to try these data and work in this domain and want to span actually in knowledge in this domain, can actually make use of these pipeline and can go through it. So these are my general remarks for the workshop, and thank you all for joining this group so that we can scale in every possible domain and learn from each other. Thank you.
Thank you, Dr. Neha. Dr. Om Prakash, please, your comments for the workshop.
Thank you very much, ma'am, for letting me speak. So this workshop was the speaker was very much experienced, and they shared very valuable knowledge. As I discussed with Sir Ashish sir earlier, who joined, that the infrastructure they were telling about in India, which is done by NSM, it is only the people who are involved, they know. But from this workshop, we know that how much work has been done and what is the indigenous work by our people has done in this area. that's a really great thing. Second thing that about this workshop is second workshop, and this field is so much big that if we allow 100 speakers also, so they will talk about the different domain which is unknown to people. If in future, if we want to, we are planning to keep one more workshop, then my suggestion will be to keep some hands-on session for people, student who are new to in this field, because the feeling or the experience this genome data from the seeds, what is actually inside this, and how we process, surely this will give benefit to many students.
Thank you, Dr. Om Prakash. So now Dr. Karthikeyan is visible. I am hoping we are audible to you, Dr. Karthikeyan. We are audible to you?
Ma'am,
Yeah,
can you
yeah.
hear me? Because I'm
Yes.
joining with mobile.
Yeah, through mobile.
My laptop connection.
For others,
Yeah,
voice is
hanging.
clear.
Can you hear me?
Yes, sir. Voice
Yes, sir.
is
Yes, sir.
clear.
We can hear you. Can please continue.
Yeah.
Hello.
Please give some remarks for the workshop, sir.
Maybe you can switch off your video, sir.
Sir, not audible.
Sir, you may please switch off the video, then audio will come clear.
So I have some problem with my network. Can you hear me?
Yes, sir.
Hello?
Now it is okay.
Yeah, now fine.
Okay, I will try to speak, and I also will try to join, if possible, through laptop. My point is, today morning I attended the talk by CDAC expert. It was very nice. So now the question is, people developed the tools bits and pieces here and there, and everybody claims that some part they did, both academic and also in industry. It was very wonderful eye-opener workshop for all of us. The next, right now, I don't know what was the discussion going on. My recommendation or my feeling is that we have to go through each and every minute of this workshop as a team, at least the people who are, all the people involved in Bharat Agri-Grid. Okay, so I think the participants are not there in this meeting, or participants are
Sir,
there?
participants are there. Through YouTube, there are participants available. Apart from that, also few participants joined here.
So my request is, please take the feedback from all the participants. The conference is very nice, and this type of conference should go on, and then it will be an eye opener for faculties and the students or participants across the country. So I think I don't want to give any other comments right now. What we can do is, after the meeting, we can have a minutes of the meeting that can be circulated based on the input received from all the experts.
Yeah, yeah.
Thank you, madam. I'm sorry, I
Thank you.
thought it is a
No, thank
group
you,
of 4
sir.
people. Okay.
So, Dr. Ayan, please give some remarks for this workshop. Dr. Ayan from IIT Jodhpur. Dr. Ayan, are you there? I think he's not there. Dr. Ratnapaki.
Yeah, so as I'm since the last 2 days, it has been very exciting since the starting of panel discussion and the type of the leadership what we have seen the distinguished guest in the panel discussion. It was amazing, and everybody has expressed their support, and so it was very exciting to see the support from all the guests who joined in the panel discussion. One thing I would say that as we are planning to help the breeders developing varieties, so still there is a big gap when the genome sequence is available and the information reaching to the breeders. It takes a huge time and also it's not easy. So right now the breeders are not very well connected with all the tools, and so this workshop focused on in these areas, and I'm sure the new tools what will be available will help in developing the new varieties in different crops. So the gap between the genome sequence and the technology available to the breeder, we can fill it with the new information, and that will be very useful for the agriculture sector. I'm very confident and very excited to see the discussion since last 2 days. Thank you.
Ma'am, I want to tell that this workshop is very nice and it is of, I think, unique kind, and it is timely. So if you all work together, we can make it a reality. So I congratulate all the participants and experts who participated in this meeting, and also the experts who guided us. So it's a fantastic and successful meeting according to me.
Yeah, there are experts available from CDAC who have given talk in the morning and afternoon. So we
I
learned.
I liked the talk of Sandeep Malviya. So he has given very nice workflow from sequence to interpretation and pattern recognition, and he also discussed very important points. The size of data. Actually, I could not get a chance to speak to him, question him some few things. When we talk about the kilobyte, megabyte, it's okay. When we talk about terabyte, exascale, something like that, one is storage problem he discussed, and there is something called a network problem. There is a bandwidth problem. So then he explained very nicely how this can be tackled using the distributed cluster architecture and other things. It was very nice. So these type of things should go on because we are going to implement in a practical way. So I think Dr. Malviya can comment about this, what I am asking about the bandwidth with respect to storage, if he is available.
Yes, sir. I would like to answer.
Only one question. I'm sorry, this is not the question and answer session for the
Yes.
participants. I'm asking
Yes.
no problem.
Hello. Hello.
Yes, Sandeep, we can hear you. Please.
Okay. So your question about the bandwidth. So, sir, that was what I was addressing, because when we develop a tool HBAT, so what happened, and we in our group there are people who are expert in MPI. So if there are suppose 100 processes are simultaneously running in MPI process, at the time there is a communication between the processes happening. So as number of processes is increasing, the number of communication will also increase. So due to this, what will happen? If you look for any application which will scale over petascale or exascale, definitely there will be at least 1,000 process which will be communicating to each other, passing the messages. So even though your network is efficient, like InfiniBand, you can solve that your message transfer is almost very good efficiency is there. But the number of messages which will exchange among the process, it will somewhere saturate the system. So and there will be a lot of blocking call in that scenario, like after sending I'm waiting for something, or unless data is received I cannot compete further. So this kind of solution, like for MPS, this kind of application, bioinformatics application, scale up to certain extent. That is what my hypothesis is. Like they can scale to maybe up to tera scale, they can scale, but beyond that their scale, if you see the benchmarking, it is saturated. The linear speed up becomes the logarithmic speed up. So the point here is that, so up to the point where the application is giving the linear scalable, beyond that increasing the number of processes doesn't make sense. But the multiple instances of those kind of application if we run, and these kind of tools if we run in a pipeline manner, like in a pipeline execution, then we will get the overall efficiency from the system, and there will be limited processes communicating to each other. So there will not be the bandwidth issue. And in case of map reduce scenario, what happens, that it is a data parallel application. So during that data parallel there is not very much communication. If you see the architecture of Hadoop MapReduce, so mapper is generating the data, reducer is somehow aggregating and making average or something, that kind of operation to it. So at reducer level there is some communication is happening, but that is up to certain level. But in MapReduce scenario, the data is so big that it doesn't fit into the memory, so that the spillover of the memory happens and the data is again fed to the disk scenario, where the performance get compromised when the disk come into picture instead of memory. So my hypothesis was that up to the whatever level the tera scale or petascale applications are giving linear scale, up to certain that extent only we should utilize them, we should scale them in the while running in the cluster, and then we make a pipeline of those tools in a workflow environment, and then we should execute a pipeline over exascale cluster instead of executing a single tool. So we can somehow limit the utilization of memory as well as solve the problem of disk as well as the main memory. So that is what my observation when I develop these many tools or algorithms. This is my observation. That is what I
Yeah,
put.
I agree with you. My actual question, maybe it was misunderstood. My question was, there is a main memory, there is a GPU memory, there is a storage data 2 GB per file that
Yes.
we are downloading per genome, for example. Right. So when we go in terascale and petascale and hexascale, so the entire data should be visible to the processor. In that context, I was asking, still some problem needs to be solved. I
Yes.
am telling you in that context. So whatever the approach you mentioned is MapReduce, distributed computing, and data chunking and bringing back, developing the doing the calculation and giving the pattern. I absolutely agree with you. But still, there is a scope for improvement. Say, for example, normal hard disk versus SSD hard disk. So the bandwidth between the data going from memory to the storage, and so now we have to look into that speed. And then GPU memory, it goes in 150 GPPS or something like that. So when we handle GPPS of data, especially one particular genome of one particular crop, say for example, soybean or rice or something, it's a huge data. So as a single snap, how to handle that data, that still the problem needs to be solved. And there is still opportunity for all of us to work together to make it happen. That was my point. You very nicely explained what are the issues and other things. I'm really sorry to take this to a very technical level.
No, sir. You're welcome, and thank you for putting this problem to my notice. Even we'll work further on this kind of scenario because we are having some discussion with ISRI also. So we are going to deploy our Anvaya, and they had put some requirement for their custom tools. They need to be developed for the analysis of agricultural data. So when we will discuss with them, we will address this kind of scenario in near future. That's for sure.
Madam, sorry I took a long time to ask this interaction, but this is very, very critical. Until unless this works, and the grid will never work, because there is a bandwidth between the user and the computer, the server, and then server to the common public domain database where people give the query and download. And there is a big bandwidth issue is there. So that needs to be addressed. Only CDAC people can help us in that, because we are going on NKN and NSM architecture. That's why I asked this critical question. The success of any project in NSM depends upon how much data, how we are going to process in a distributed system, especially Hadoop and Spark type of thing. Thank you so much, Dr. Malviya. It's very nice.
Yes. Thank you, sir.
Thank you, Dr. Karthikeyan. These questions are very important for like all participants, and we also struggled a lot when we connected with the supercomputer. We accessed the supercomputers. So it took months of time to deploy that Apache Spark, establishing that setup, and then started actually using that one. So we in fact called many CDAC people also through Dr. Ashish Kulbekar. Thanks to Dr. Kulbekar. And now let's move to another person. Ayan, are you there, Dr. Ayan? Are you there, Dr. Ayan, IIT Jodhpur? I think he again left. Okay, so let's move to the participants. Preeti Jha, your comments. My scholars, please share your comments for this workshop.
And we have got so many ideas through this workshop, and in future means next task, there are so many tasks we need to do. Amit sir has guided us so many things in this time, means the days we are working with this Bharat Agri-Grid. So there are so many ideas which Amit sir, Karthikeyan sir, Sanjay sir, and Ayan sir. Everybody has given so many ideas, so that needs to be incorporated in our team. And I am very grateful to this, and I will take it into account to the work in that flow, whatever I have not worked.
Thank you, Preeti.
Thank you.
Suchitra, please.